Earth is no longer holding still. Our best instruments are catching it in the act. Satellites, ocean buoys, and magnetic observatories all agree on one unsettling signal. The baseline is shifting, and it's shifting fast. So what exactly is changing right now? And how do we separate natural cycles from human fingerprints before the numbers outrun the story? For most of human history, Earth felt like the stable stage beneath the drama of the sky, reliable, familiar, and slow to change. But now the instruments watching our planet are converging on the same unsettling pattern. Signals that repeat across systems, across oceans, across hemispheres. A tide gauge ticks upward in a harbour, and a satellite sees the same rise from orbit. 2 methods, 1 story. Argo floats slip through the dark water column, recording heat where no human eye can follow, an archive written in temperature and salt. Over ice sheets, gravity itself becomes a scale, weighing loss in silent increments, while cameras watch bright margins retreat. This film begins with a question that refuses easy answers. What measurable changes are happening to Earth right now, and what do they mean? Are we witnessing the familiar swing of natural cycles, orbital rhythms, volcanic pulses, solar variability, or the fingerprint of a new forcing? And when the noise is stripped away, what do the best observations and models say is actually happening? Without exaggeration, without speculation. Because Earth has always been a world in motion. Plates drifting, climates turning, coastlines advancing and retreating across deep time. The unusual part is not change itself, but the rate. How quickly multiple indicators move together, and how consistently they keep moving. In the modern record, the planet speaks in numbers, and those numbers carry a kind of coherence that is difficult to dismiss. We will follow the evidence where it is strongest and linger where uncertainty remains, because uncertainty is not a weakness, it is part of the measurement. We will watch how instruments are calibrated, how independent data sets cross-check each other, and how a trend earns the right to be called real. And we will ask, again and again, the simplest question science can ask: what would we expect to see if this were only nature? First, we widen the lens until Earth stops looking still, until it becomes a dynamic world inside a dynamic cosmos. Then we trace the planet's energy ledger, a quiet accounting where small imbalances accumulate into enormous stored heat. We descend into the ocean, the great memory of the climate system, and we learn why warmth there changes sea level even before ice melts. From that hidden heat we move to the cryosphere, where reflective surfaces can vanish, revealing darker ones that drink in sunlight. We step into the atmosphere's restless machinery, where thermodynamics turns warmth into water vapour and shifts the odds of extremes. And then we enter the chemical story. Carbon moving invisibly between air and sea, altering not only temperature but the very character of seawater. Along the way, we confront other signals people fear and often misunderstand. Earth's magnetic field in motion, the shifting ground of earthquakes and volcanoes, and the changing conditions in the space weather above us. Each chapter holds a different kind of evidence, and each demands the same discipline: separate coincidence from causation and wonder from proof. By the end, the mystery does not dissolve into panic or into comfort. It resolves into clarity, a planet responding to an altered balance of energy and chemistry, with consequences that unfold on human timescales and beyond. And with that clarity comes the only real power we have: deciding what happens next, with eyes open. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. This is a journey across sky, sea, ice, rock and field, guided by instruments that do not guess and records that can be checked. What you will see is not a single catastrophe, but a pattern, one that becomes legible only when the whole planet is measured at once. For most of human history, Earth felt steady, while the sky carried the drama. Seasons returned on schedule, coastlines seemed fixed, and the ground underfoot promised permanence. In village memory, the shoreline was a line you could trust, and the hills looked as old as time, yet Earth was never still, and the record of deep time proves it. The rocks keep receipts, layer by layer, mineral by mineral, if we learn how to read them. Continents drift a few centimeters each year, driven by mantle heat and plate tectonics. That motion sounds trivial, but over 1 million years it redraws oceans and rearranges climates. Beneath the crust, Convection moves hot rock upward and cooler rock downward, like a slow, viscous engine. New seafloor forms at mid-ocean ridges, while old plates sink at subduction zones, carrying water and carbon into the mantle. The planet's surface is recycled, and the recycling leaves scars we can map from space. Ice ages come and go as orbital cycles reshape sunlight over thousands of years. Small changes in Earth's tilt, wobble, and orbital shape shift where summer heat lands, especially at high latitudes. Those shifts nudge ice sheets forward or back, and then feedbacks take over. Brighter ice reflects more sunlight, darker oceans absorb more, and the balance can tip in either direction. Volcanoes and asteroid impacts punctuate long eras, then ecosystems rebuild across millennia. A single eruption can shade the planet for a few years, while a large impact can rewrite the biosphere for ages. The planet changes, but it usually changes on timescales that outlast a lifetime. That slow pace shaped human intuition, and it taught us to treat Earth as a stable stage. We built calendars around predictable seasons, and we built cities around the assumption of a familiar coast. Even when disasters struck, they felt local: storms, droughts, earthquakes, events that came and went. Deep time, by contrast, is a different kind of weather, and it moves with a different clock. Now we live inside a different kind of evidence, and it arrives with timestamps. Instruments ring the world, and they measure change in real time day after day. Satellites weigh ice and water from space, floats sample the oceans, and observatories track gases, heat, and fields. Some sensors stare downward at Earth's surface, while others watch the planet's glow in infrared at night. The story they tell is not a single anomaly, but a pattern. It is a pattern that repeats across independent systems, even when the sensors were built for different purposes. Something really unusual is happening to Earth, and the first rule is restraint. No conspiracies, no secret plots, no viral claims that outrun the data. We follow measurement, uncertainty ranges, and the physical mechanisms that connect cause to effect. Where the evidence is strong, we say so, and where it is weak, we say that too. This is how science earns trust, by showing its limits as clearly as its conclusions. Unusual has a scientific meaning, and it is not a feeling. It means the rate of change is high compared with a recent instrumental record. It means the signal is statistically rare given known variability and measurement error. It means independent datasets move in the same direction, even when they are built differently. In practice, it means trends persist after you account for seasons, cycles, and noise. It means the same acceleration appears in places that do not share the same instruments, funding, or processing pipelines. A single thermometer can be wrong, but networks are harder to fool. A single station can drift because of shade, sighting, or maintenance, and those problems are real. Yet when thousands of stations agree after careful corrections, the odds of shared error shrink. A single satellite can drift, but overlapping missions cross-check their baselines. Engineers compare sensors against reference targets, and analysts watch for tiny calibration shifts that could mimic trends. A single model can mislead, but multiple lines of observation can strain what is plausible. The mystery begins when different tools agree on the same acceleration, quietly, repeatedly, and without coordination. We start with a slow Earth, because it sets the background. Plate boundaries migrate, oceans open and close, and mountains rise as crust thickens. In some places, continents collide and crumple, building ranges that steer winds and monsoons. In other places, rifts pull land apart and new seas are born. The wobble of Earth's axis and the shape of its orbit modulate incoming sunlight. Past climates swing between extremes, and the planet remains habitable through feedbacks that usually stabilize over long spans. Carbon cycles between air, ocean, rock, and life, and that cycling normally takes thousands to millions of years. Then we cut to the fast Earth, because it is what the instruments see. Global average sea level rises year after year, and the curve bends upward. That bend matters because it suggests acceleration rather than a steady climb. Heat accumulates in the ocean, and the upper layers warm with measurable persistence. The ocean is Earth's main heat reservoir, and it hides change in plain sight. Ice sheets lose mass, and mountain glaciers retreat across regions that once held steady. In satellite images, the edges of ice pull back like a slow exhale, exposing darker ground and meltwater blue lakes. The key is not one graph, but convergence across methods. Tide gauges measure sea level at coasts, and satellite altimetry measures it across the open ocean. Gauges feel the local world, storms, land subsidence, uplift, while satellites see the global surface like a moving ruler. Ice cores preserve ancient air, and modern sensors measure today's atmosphere directly. Bubbles trapped in ice hold past CO2 and methane, and they let us compare then to now. Reanalysis blends observations with physics, and it reveals coherent patterns across decades. It is not magic, just disciplined bookkeeping that forces the atmosphere to obey conservation laws. This documentary is built on an observational backbone, and that backbone has a history. NASA and ESA satellites provide global coverage, repeated often enough to detect trends. The space age turned Earth into a measured object, and it changed what we could know: grace and grace. Follow on track. Gravity changes that reveal shifting water and ice mass. They do it by measuring the distance between twin spacecraft with extraordinary precision, as Earth's gravity subtly speeds one up and slows the other down. Sentinel missions map land, ice and oceans, and they show change at scales no field campaign can match. From orbit, a retreating glacier is not a rumour, it is a boundary you can trace. JSON altimetry measures sea surface height with centimetre precision across the planet. It sends radar pulses to the ocean, then times their return, and the timing becomes a map of sea level. Argo floats profile temperature and salinity through the upper 2 kilometres of the ocean. They drift with currents, dive, rise, and transmit data by satellite, building a 3-dimensional picture of heat and salt. Mauna Loa's CO2 record anchors the modern carbon story with a continuous calibrated time series. It began in the late 1950s, and its sawtooth rhythm, up in winter, down in summer, reveals the breathing of the Northern Hemisphere. Seismic networks listen to the crust, and magnetometer arrays monitor the restless geomagnetic field. These systems do not all point to the same cause, but they share a theme. Earth is active, and it is measurable. Paleoclimate proxies extend the context beyond the short instrumental window. Ice cores, tree rings, corals, lake sediments, and speleothems encode past temperatures and rainfall. A tree ring can record a drought year in its narrowness, while a coral skeleton can archive sea temperature in its chemistry. Lake mud layers can preserve floods, fires, and dust, stacked like pages in a book. They do not replace modern measurements, but they frame what variability looks like without satellites. They help separate normal swings from shifts that stand out, and they remind us that nature can change abruptly under the right conditions. Uncertainty is not a weakness, it is part of the method. Every dataset carries error bars from instruments, sampling, and processing choices. Satellites must correct for orbital decay, sensor drift, and atmospheric interference, and those corrections are openly documented. Ocean floats have gaps, and polar winters can hide the surface from view, so analysts quantify what is missing. We track those ranges because they define what we can claim with confidence. When signals exceed uncertainties across multiple systems, the case becomes harder to dismiss. The goal is not perfection, but transparency, so anyone can test the chain of reasoning. The central question is not whether Earth changes, because it always has. The question is what is changing now, at what rate, and for what reasons, which signals fit natural cycles and which require additional forcing. What do the best observations and models say these signals mean, without exaggeration? If we misread the present, we misunderstand the future, and we misjudge the risks we are already committed to. The tension comes from timing and alignment. Several independent indicators are changing in the same direction at unusual rates. Energy is accumulating in the climate system, and the ocean stores most of it. That stored heat is not abstract, because it expands seawater and feeds evaporation. The atmosphere is changing composition, and the chemistry has consequences for heat and life. When the air's infrared opacity increases, nights cool less efficiently and the baseline shifts. We do not treat this as a single-issue story, because Earth is not a single-issue system. Earth's life support systems are coupled through energy balance, chemistry, and circulation. A small shift in one place can amplify elsewhere through feedbacks. When thresholds are crossed, change can cascade faster than intuition expects. The unsettling question is not whether feedbacks exist, but which ones are already engaged, and how strongly. Energy balance is the simplest accounting, and it governs everything downstream. Incoming sunlight is mostly stable, but the fraction retained by Earth can change. Greenhouse gases trap outgoing infrared radiation, and aerosols and clouds complicate the picture. Some aerosols reflect sunlight and cool, while others absorb and warm, and their lifetimes are short. Ice and snow reflect sunlight, and their loss lowers albedo and increases absorption. In plain terms, a darker planet runs warmer, even if the sun stays the same. Chemistry adds another layer of constraint and risk. Carbon dioxide persists, and it accumulates when emissions exceed uptake by land and ocean. Once added, a significant fraction remains for centuries, because the slowest sinks involve rock weathering and deep ocean processes. Methane is shorter-lived, but it is potent and tied to both biology and industry. It leaks from fossil fuel systems, rises from wetlands, and spikes during certain climate conditions. Ocean uptake buffers the atmosphere, but it also acidifies seawater and stresses ecosystems. Dissolved CO2 forms carbonic acid, which lowers pH and reduces carbonate ions that many organisms use to build shells. Feedbacks decide whether a push stays small or grows. Water vapor increases with warming, and it amplifies the greenhouse effect. Warming can weaken ice, darken surfaces, and expose more heat-absorbing ground and water. In the Arctic, melt ponds and open water absorb sunlight that ice once reflected, and the season of absorption lengthens. Circulation shifts can move rain belts, alter drought patterns, and reshape wildfire risk. These are not separate stories, because heat, moisture, and wind are linked by physics. The point is not to predict doom, but to map mechanisms. We separate what is measured from what is inferred, and what is inferred from what is projected. We look for causal chains that respect physics, conservation laws, and known timescales. Alarmism is easy, but disciplined inference is harder and more useful. It requires patience with uncertainty, and it rewards careful attention to what the planet actually does. Some changes are noisy, and some are unmistakable. Weather varies day to day, and climate emerges in averages and trends. A single storm can be spectacular, yet it may say little about the long-term baseline. Earthquakes strike without warning, but seismic catalogues reveal long-term patterns of strain. They show where plates lock, where stress accumulates, and where energy is released. The magnetic field wanders, and magnetometers capture its drift without claiming it controls everything. The field's slow changes matter for navigation and radiation belts, even if they are not the driver of today's warming. The unusual part is the coherence across domains. Heat content rises, sea level rises, and ice mass falls, and the directions match. Atmospheric greenhouse gases rise, and isotopic fingerprints help trace sources. Carbon from fossil fuels carries a distinctive signature, because ancient organic matter is depleted in carbon-13. The planet's radiative imbalance is measured, and it aligns with the warming stored in the ocean. When independent budgets close, energy in, energy out, heat stored, the story becomes less about debate and more about accounting. We also confront the limits of the record, because honesty demands it. Satellites span decades, not centuries, and some trends may hide earlier variability. Proxies extend further back, but they blur details and require careful calibration. A tree ring may reflect temperature, moisture, or both, depending on the region, so interpretation is careful work. Models are not oracles, but they test whether mechanisms can reproduce observed patterns. They are laboratories made of equations, and they let us ask, if this cause is real, does it produce what we see? The best answers come from combining all three, because each one corrects the other's blind spots. So we set the rules for what follows and we make them explicit. Every claim must point to a data set, a method, and an uncertainty range. Every mechanism must connect cause to effect without leaps. Every comparison must respect timescale, baseline choice, and known natural cycles. If a claim cannot survive those constraints, it does not belong in the narrative, no matter how dramatic it sounds. We begin at the widest scale because it organizes the rest. From a cosmic vantage point, Earth is an energy processing system in a variable solar neighborhood. The sun provides the input, space receives the output, and the difference accumulates as heat. If the budget shifts, everything on the surface eventually responds. From orbit, Earth's day side gleams white with clouds, while the night side glows faintly in infrared, an invisible portrait of energy leaving the planet. The first visible signs of imbalance appear in the air. The atmosphere changes quickly, and it carries the fingerprints of combustion and land use. It also controls how much heat escapes to space each night. Satellites can measure outgoing long-wave radiation, and they can detect subtle changes in spectral bands where greenhouse gases absorb. Ground stations sample air directly, and they reveal trends that do not depend on any single instrument. To understand what is happening to Earth, we start where the imbalance becomes measurable. The air is thin, but it is decisive, because it is the gatekeeper between the warm surface and cold space. Next, we move from the planet's energy budget down into the atmosphere, and we follow the numbers. We start with the slow Earth, because it sets the background. Now we narrow to a faster ledger that updates every second, even when nothing looks different outside your window. Climate change begins as accounting, energy in, energy out, and the difference, if it persists, becomes history. Earth's budget starts with sunlight, a stream of shortwave radiation arriving after 8 minutes of travel through space. The sun's output is not perfectly constant, yet over decades it is steady enough to treat as a baseline for the ledger. At the top of the atmosphere, that sunlight arrives like a bright, even wash across the planet's disk. What happens next depends on surfaces, particles and clouds, each one a gatekeeper deciding what stays and what escapes. Some sunlight is reflected back to space by clouds, aerosols, ice, and bright land, and the planet's reflectivity is called albedo. In visible imagery, albedo is the difference between a white shield and a dark sponge. A deck of marine clouds can flash like polished metal from orbit, while open ocean looks almost black, swallowing light. Albedo is one of Earth's main control knobs, and it can shift with seasons, storms, and long-term change. The rest of the incoming sunlight is absorbed by the surface and atmosphere, then converted into heat through molecular motion. Over land, that energy warms soil and rock, and it drives evaporation that carries heat invisibly into the air. Over ocean, it penetrates the surface layer and is stirred downward by winds and waves. Even the atmosphere absorbs some sunlight directly, especially where ozone and aerosols intercept it. A warm Earth must radiate energy back to space to balance the books, and it does that mostly as infrared radiation. The surface emits infrared upward, and so does the air itself, because gases and clouds also radiate when they are warm. If outgoing infrared equals absorbed sunlight, average temperature can stabilize around a long-term mean. If outgoing infrared is reduced, even slightly, the system gains heat until a new balance is reached. This is the greenhouse effect, stripped to its essentials but not stripped of its mechanism. Certain gases are mostly transparent to incoming sunlight, so the shortwave energy reaches the surface efficiently. Those same gases absorb specific wavelengths of outgoing infrared, because their molecular vibrations and rotations match those energies. After absorption, the atmosphere re-emits infrared in all directions, including back downward, so the surface and lower air retain more energy than they otherwise would. Visually, you can imagine the planet at night, glowing in infrared like a living ember. Some of that glow escapes directly to space through clearer spectral windows, while some is intercepted and rerouted. The atmosphere is not a solid roof, and heat still leaves. The pathway simply becomes longer and more selective. That subtle rerouting is enough to change the global balance. The greenhouse effect is not a theory invented for modern politics, and it did not begin with satellites or supercomputers. In the 19th century, scientists such as Fourier, Tyndall, and Arrhenius helped establish that certain gases absorb heat radiation and can influence climate. Their tools were crude by today's standards, yet the core physics has only been refined, not overturned. Without the natural greenhouse effect, Earth would be far colder, and liquid oceans would be rare. So the question is not whether greenhouse warming exists, because it is measured in laboratories and observed in the sky. The question is what happens when humans thicken that infrared blanket quickly, in decades rather than millennia. How fast can the system adjust, and where does the accumulating energy go while it does? The key term is radiative forcing, a change in Earth's energy balance caused by a driver outside the immediate temperature response. Add greenhouse gases, and you create a positive forcing that reduces outgoing infrared at the top of the atmosphere. Add reflective aerosols and you create a negative forcing that reduces absorbed sunlight. Change land cover and you can shift albedo and moisture, altering both shortwave reflection and longwave emission. Forcing is the push, but the climate response is the motion that follows, and it is shaped by feedbacks. Water vapor rises with warming because warmer air can hold more moisture, and water vapor is itself a greenhouse gas that strengthens infrared trapping. Snow and ice retreat and lower albedo, increasing absorbed sunlight and accelerating regional warming. Clouds can cool or warm depending on altitude, thickness, and droplet physics, and their net effect remains a major uncertainty even as measurements improve. Carbon dioxide matters because it is abundant, long-lived, and strongly tied to combustion, which makes it a reliable tracer of industrial activity. It does not absorb uniformly across the infrared, yet its main bands are influential, and its effects broaden as concentrations rise. Methane matters because it is potent and rising, even though it oxidizes faster than CO2 and eventually becomes CO2 and water. Nitrous oxide matters because it's powerful per molecule and linked to agriculture and industry, and it persists long enough to accumulate. Each gas absorbs in different infrared bands, and together they widen the range of trapped heat. Where one gas leaves a partial window, another can narrow it, and the combined effect is a thicker, more complex filter. This is why the atmosphere's composition matters as a system, not as a single number. The ledger is written in spectra, not slogans. The documentary's central question demands measurable signals, not just plausible stories. If greenhouse gases are driving a persistent forcing, we should see them rising in the air itself. If the forcing is real, we should measure less energy, leaving to space in key spectral bands where those gases absorb. If Earth is retaining extra heat, the climate system should store it somewhere, even when surface temperatures wobble. We have direct measurements of greenhouse gases, and they form one of the cleanest modern records. In 1958, Charles David Keeling began precise CO2 monitoring at Mauna Loa, high above local pollution and vegetation effects. The curve climbs year after year, with a sawtooth seasonal cycle driven largely by Northern Hemisphere plant growth and decay. That pattern is not a model output, it is air-sampled, calibrated, and archived with meticulous care. In the visuals, the Keeling curve is almost hypnotic, like a heartbeat that keeps rising. Each annual dip is photosynthesis pulling carbon from the air, and each rebound is respiration and decay returning it. The long-term climb, however, is the signature of a new source added to the system. The atmosphere is remembering what we burn. CO2 rises are not just numbers, because they carry a chemical fingerprint that points to source. Fossil carbon is depleted in carbon-13 because ancient plants favoured carbon-12 during photosynthesis, and that preference is preserved in coal, oil, and gas. As fossil fuels are burned, atmospheric carbon-13 declines relative to carbon-12, a shift measured with high precision. Oxygen also drops slightly as combustion consumes it, matching expectations from burning carbon in air. That oxygen signal matters because it closes a separate part of the accounting. If CO2 were rising mainly from ocean release or volcanic outgassing, the oxygen trend would not match combustion in the same way. Instead, the paired changes behave like a forensic record, written in ratios rather than headlines. The chemistry does not argue, it simply accumulates. Methane and nitrous oxide show their own upward trends, and they complicate the story in instructive ways. Methane has multiple sources, including wetlands, agriculture, landfills, and fossil fuel systems, and its concentration responds to both emissions and atmospheric chemistry. Its isotopes and co-emitted gases help separate biogenic from thermogenic contributions, though the boundaries are not always clean. Nitrous oxide tracks fertilizer use and industrial processes, and it persists long enough to build steadily in the background. These concentration records answer one part of the question, but they do not finish the proof. The atmosphere is changing composition in a direction that increases infrared opacity, and that is a necessary step. The next step is harder, because it requires measuring the planet's energy budget itself. We must show that the ledger is actually out of balance, not just that the ingredients changed. From space, satellites measure radiation at the top of the atmosphere, where the planet meets the cold sink of space. They estimate incoming solar energy, an outgoing reflected shortwave, and emitted longwave, scanning Earth in repeated swaths. The instruments are complex and calibration is difficult, so uncertainty is real and openly quantified. Yet multiple lines of evidence converge on the same sign. Earth is absorbing more energy than it emits. The imbalance is small compared to the total flow, but it is persistent, and persistence is what turns a whisper into a force. Think of it as a quiet fever, rather than a sudden blaze, a few extra tenths of a watt spread over every square meter. A small surplus, sustained over years, becomes an enormous amount of stored heat when multiplied by the planet's surface area. Earth does not need a dramatic imbalance to change. It only needs a steady one. We can cross-check the satellite budget with the planet's heat storage because energy cannot vanish. If more energy comes in than goes out, the excess must accumulate in the Earth system, even if it hides from casual observation. It can warm the air, warm the land, melt ice, and heat the ocean. The accounting closes only if the storage matches the measured imbalance within uncertainties. This is where the ocean becomes central, not as scenery, but as evidence. More than 90% of the excess heat goes into the ocean because water can absorb vast energy with modest temperature change. The atmosphere warms quickly but holds little heat since it has low mass and low heat capacity. Land warms and stores energy too, but its volume is limited and its heat transport is slower. Ice consumes energy without warming much because melting requires latent heat, a hidden payment in the ledger. You can pour energy into ice and see little temperature change until the phase shift is complete. That is why melting can accelerate even when air temperatures fluctuate around familiar values. The ocean, by contrast, is vast, dense, and mixed over time, so it becomes the main reservoir for the imbalance. Water's heat capacity is high, and the ocean's mass is enormous, so together they dominate the storage term in Earth's budget. That dominance also creates lag because the surface does not instantly reflect the full forcing when the ocean is absorbing heat below. Heat is transported by turbulence, currents, and overturning, and those processes take time. This lag is not a loophole, it is a physical expectation that can be measured. For decades, ocean measurements were sparse and uneven, and the gaps mattered. Ships sampled along routes, and records clustered where commerce travelled, leaving broad regions under-observed. Early instruments like expendable bathythermographs expanded coverage, but introduced their own biases that later had to be corrected. Then the observing system changed, and the ocean began to reveal its trend with far greater clarity. Argo floats began profiling temperature and salinity across the global ocean, turning the sea into a monitored volume rather than a set of scattered points. They dive, drift, rise, and transmit, building a consistent picture of upper ocean heat content across seasons and basins. On screen, an Argo float is small against the ocean scale, yet its data threads into a planetary tapestry. Thousands of them, cycling quietly, make the invisible measurable. Ocean heat content is not a headline-friendly metric, but it is a decisive one because it integrates variability. Year-to-year surface temperatures can stall or surge, and weather can distract the eye with noise. The ocean, however, keeps accumulating heat, and that accumulation is the ledger's most direct consequence. When the ocean heat curve rises steadily, it is hard to argue the planet is not gaining energy. The ocean also explains why surface warming can appear uneven, even when the global balance is consistent. Heat can be sequestered deeper by mixing and circulation, shifting where energy resides without changing the total. Winds can push warm water around, altering regional patterns and temporarily masking warming in one place, while enhancing it in another. A decade with strong ocean uptake can mute surface warming. A decade with reduced uptake can let surface temperatures jump. Natural variability is real, and it is part of the story we must not exaggerate, because it is often mistaken for reversal. El Niño and La Niña shift heat between ocean and atmosphere, changing rainfall patterns and storm tracks along the way. During El Niño, the tropical Pacific releases heat and global surface temperatures often spike. During La Niña, the ocean draws heat down and surface warming can slow. ENSO changes the distribution of heat, not the long-term direction of the energy ledger. The ledger cares about the total, not the temporary location, and the ocean keeps the receipts. This is one reason the ocean record is so valuable when public attention focuses on short runs of surface temperature. The question becomes unavoidable. If the heat did not leave, where did it go? Volcanoes also modulate the budget, and their fingerprints are sharp enough to teach the physics in real time. Large eruptions inject sulfate aerosols into the stratosphere, where they can persist for a year or two, reflecting sunlight and cooling the surface. The cooling is measurable in temperature records and in radiation measurements, a brief dimming of the planet's intake. As the aerosols fall out, the masking fades and the underlying forcing reasserts itself. Volcanic dips are not contradictions. They are expected perturbations in a system with multiple forcings. They also remind us that aerosols can cool while greenhouse gases warm, and the net effect is the sum of competing terms. The atmosphere can be both a mirror and a blanket, depending on what we add to it. The ledger does not care about intent, only about optical properties. Solar cycles add another layer of variability. subtle but measurable in precise instruments. The Sun's output changes slightly over the 11-year cycle, and that change can influence upper atmosphere chemistry and circulation. Yet the magnitude is small compared to the forcing from rising greenhouse gases over recent decades. Solar variability can shape wiggles, but it does not explain the sustained accumulation of heat. To separate variability from trend, we compare many datasets because no single instrument sees everything. Surface thermometers, satellite temperature retrievals, ocean heat content, sea level, ice mass, and humidity all provide different windows into the same system. Each has biases and corrections, and each has independent teams checking methods and assumptions. When they align on a long-term rise in stored heat, the coherence becomes the signal. The energy imbalance also leaves spectral fingerprints, and these are among the most elegant pieces of evidence. Greenhouse gases absorb at specific infrared wavelengths, so outgoing radiation decreases in those bands while other bands change differently. Satellites can detect changes in the spectrum over time, showing the atmosphere's selective grip. At the same time, downward long-wave radiation at the surface increases, measured by ground instruments under clear skies and cloudy ones. These are not just temperature changes, they are changes in the pathways by which heat escapes. They tell us not only that warming is occurring, but how the energy is being redirected through the atmosphere. The story becomes less like a thermometer and more like a fingerprint analysis. In climate science, the how is often as important as the how much. A common misunderstanding is to treat the greenhouse effect as a simple lid, as if heat is trapped and nothing leaves. In reality, the atmosphere still radiates to space, mostly from higher, colder layers where the air becomes thin. Add greenhouse gases and the effective emission height rises, because infrared photons travel a shorter distance before being absorbed. Higher altitude is colder, so it emits less infrared for the same wavelength range. To restore balance, the system warms until emission increases enough to match incoming energy again. That warming increases infrared emission from the surface and the atmosphere, and it also changes water vapor and clouds, which feed back into the budget. The adjustment is not instantaneous, because the ocean is absorbing heat and delaying full surface response. The ledger balances eventually, but the path to balance can be long. That warming does not distribute evenly, and the patterns carry diagnostic value. The lower atmosphere warms more than the upper stratosphere, which tends to cool under increased greenhouse gases because it radiates efficiently to space while receiving less infrared from below. Nights warm faster than days in many regions because infrared trapping matters most when the sun is absent. The Arctic warms faster than the global average because of albedo feedbacks and heat transport. These patterns are not proof by themselves, but they are consistent with the physics, and they help distinguish greenhouse forcing from other drivers. They are like the shape of a footprint, not just the depth of it. When multiple expected patterns appear together, coincidence becomes less plausible. The planet begins to look like a system responding to a known kind of push. The accounting framework also clarifies what uncertainty means, which is often misunderstood as ignorance. Uncertainty in cloud feedback does not erase the sign of greenhouse forcing, because the basic absorption bands and measured concentrations remain. Uncertainty in aerosol forcing affects how much warming we should expect for a given greenhouse rise, because aerosols can offset some incoming sunlight. Measurement uncertainty in satellites is narrowed by overlap, cross-calibration, and comparison to ocean heat uptake. The goal is not perfect knowledge, because perfection is not required to close a budget. The goal is a constrained ledger that does not violate conservation of energy, and that holds up under independent checks. When different methods converge, uncertainty becomes a range rather than a doubt about direction. The fever's exact degree may vary by estimate, but the fever is there. The tension in this chapter comes from scale, because the numbers look small until you integrate them over time. The imbalance is measured in fractions of the total energy flow, yet it accumulates relentlessly across seasons and decades. Over years, it warms the ocean, even when weather makes the surface seem capricious. Over decades, it expands seawater and raises sea level, and it commits ice to melt. Sea level rise is one of the clearest downstream consequences of ocean heat, and it is measured with increasing precision. Warm water expands, and that thermal expansion adds height, even without adding mass, a quiet swelling of the ocean basin. Melting glaciers and ice sheets add mass, increasing sea level further and changing coastal risk. The ocean integrates both effects, and the curve is monitored by tide gauges and satellites. Melting ice is also an energy story, and the ledger explains why it can accelerate without theatrical temperature jumps. Ice can absorb large amounts of heat while staying near the melting point, because phase change consumes energy without raising temperature much. When ice disappears, darker surfaces absorb more sunlight, amplifying warming through reduced albedo. The energy ledger links these pieces without needing dramatic language, though the consequences can still be dramatic. Circulation shifts are harder to measure, but the mechanisms are straightforward once the budget is understood. Heat changes density, and density differences drive currents that move energy around the planet. Fresh water from melting ice changes salinity and stratification, which can alter mixing and the exchange between surface and depth. Winds respond to temperature gradients, and temperature gradients respond to forcing, so the ocean and atmosphere remain coupled engines. A persistent energy surplus nudges their patterns, sometimes subtly, sometimes in ways that become visible only after years of averaging. The system does not flip like a switch, but it does drift, and drift can reshape extremes. This is where the mysterious tone belongs, because the cause is quiet while the implications are expansive. What else changes when the planet's basic budget no longer balances? We return to the central question, because it disciplines the narrative and keeps us anchored in observation. What is measurable right now, and what is the uncertainty around it? How do we separate cycles from human influence without pretending variability is irrelevant? What do observations and models say these signals mean without speculation? The energy imbalance is the hinge, because it connects cause to effect through conservation laws. It links the chemistry of the air to the heat of the ocean, and it links small fluxes to large outcomes over time. It also gives us a way to test claims, because the ledger must close. If a proposed explanation breaks the budget, it fails. Models enter here as tests, not as crystal balls, and their role is often mischaracterized. If we input observed greenhouse gases, aerosols, solar variability, and volcanic eruptions, models reproduce the broad temperature evolution and many spatial patterns. If we remove human forcings, the long-term warming trend largely disappears in simulations, even though natural variability continues. That comparison does not prove every detail, but it strengthens attribution by showing which combination of forcings matches the observed ledger. The most important point is that the ledger is closing, and it is closing from multiple directions at once. Rising greenhouse gases are measured directly, and their fossil origin is supported by isotopes and oxygen changes. Satellites detect a top-of-atmosphere imbalance consistent with increased infrared trapping, even as instruments and analyses continue to improve. The ocean stores the majority of the excess heat, and its heat content rises across observing systems. This is why the story feels quiet at first, because the mechanism is incremental rather than explosive. The planet is not warming like an oven with the door shut. It is warming like a bank account with a small, constant deposit, compounded by time and scale. The balance grows even when day-to-day spending looks normal, and the longer it continues, the harder it becomes to reverse quickly. Next, we move from the planet's energy budget down into the ocean, and we follow the heat. If the planet is retaining extra energy, the ocean should be where the evidence accumulates first, in layers that remember past seasons. We go there not for drama, but for the cleanest record of the imbalance becoming real. We follow the heat into the deep, because the deep is where the planet hides its change. Next, we move from the planet's energy budget down into the ocean, and we follow the heat. The ocean is not just scenery, it is the main reservoir for Earth's excess energy, quietly taking in what the atmosphere cannot hold for long. Water has a high heat capacity, meaning it can absorb enormous energy with only a modest temperature change. That simple property turns the ocean into a stabilizer, smoothing short-term swings that make the air feel chaotic. When the atmosphere looks noisy from day to day and year to year, the ocean integrates change with a slower, heavier rhythm. That makes ocean heat content a clearer signal than any single year of air temperature, especially when we want to detect a persistent imbalance. This chapter stays with the central question and its discipline. What changes are measurable right now? What are the uncertainties? And what mechanisms connect them? We separate cycles that move heat around from trends that add heat to the system, because redistribution can masquerade as change. A warm patch can drift, a current can shift, and the surface can cool while the deeper ocean keeps gaining energy. The ocean's memory is not a metaphor. It is physics, stored in joules and carried by moving water. Measuring the ocean begins with a problem of scale and access, because most of it is remote, deep, and hostile to instruments. Ships can sample only where routes go, and storms and ice limit coverage in the very places where change can be fastest. Early records were valuable but uneven, and biases had to be corrected carefully to avoid mistaking method for climate. Some instruments warmed in the sun before deployment, some sampled too shallow, and some recorded temperatures with subtle offsets that only appeared decades later. The history of ocean measurement is also a history of learning how to compare imperfect snapshots. Argo changed the observing system by turning the ocean into a repeatedly sampled volume, not just a set of scattered points. Profiling floats drift, dive, and rise, measuring temperature and salinity through the upper 2 kilometers with a regular cadence. In visuals, they appear as a quiet constellation, dots across the blue, each one sinking into darkness, then returning to the light. Their global coverage reduces guesswork about where heat is accumulating, and it also reduces the temptation to overinterpret a sparse record. The network is not perfect, but it is systematic, and that is the difference between anecdote and evidence. Argo data also reveal structure, not just averages, and structure is where mechanisms hide. Heat can concentrate in certain basins, then spread through currents and mixing, leaving patterns that look like fingerprints. Salinity changes help diagnose freshwater inputs and shifts in evaporation and rainfall, because salt is conserved in ways heat is not. A fresher surface layer can signal increased precipitation, river discharge, or melting ice, while saltier water often points to enhanced evaporation. Temperature and salinity together determine density, and density controls how water stacks and flows. Ship-based measurements still matter because they reach deeper and carry long continuity, linking modern sensors to older baselines. CTD casts provide high-precision profiles that anchor calibration and detect subtle biases, especially when float sensors drift over time. On screen, a CTD rosette descends like a chandelier into black water, bottles waiting to close at chosen depths. Repeat hydrography lines show how water masses change over decades, tracing the slow migration of heat and salt through the interior. These cruises are expensive and rare, yet they are the reference points that keep the global system honest. Satellites add a different kind of ocean measurement because they see the surface everywhere, including places ships avoid. Altimetry measures sea surface height with centimetre-scale precision across the open ocean, using radar pulses timed to fractions of a second. It turns the ocean surface into a moving map of change, ridges, depressions, and gradients that mirror currents below. In a visualization, the sea becomes a textured skin, rising and falling in slow motion as if breathing. Altimetry does not measure heat directly, but it measures one major consequence with relentless clarity. As seawater warms, it expands, and that expansion raises sea level without adding mass, a process called steric sea level rise. The ocean can rise even if no new water is poured in, simply because the same water occupies more volume. Expansion depends on temperature and pressure, so a degree of warming near the surface does not equal a degree at depth. The deeper the water, the more pressure compresses it, and the less it expands for the same temperature change. Tide gauges provide the older coastal record, and they ground truth the satellite era with a human-scale perspective. They measure relative sea level at specific locations, where people live and build, and where the shoreline is a boundary between safety and loss. In archival footage, a tide staff sits beside a pier, waves slapping wood, numbers rising and falling with the pull of the moon. Tide gauges also capture storms and seasonal cycles that satellites average differently, preserving the extremes that define damage. Their limitation is also their strength. They are local, and local is where consequences land. To separate height from mass, we need another line of evidence because sea level can rise for more than one reason. Grace and grace follow. On measure changes in Earth's gravity field from space, tracking how mass redistributes across the planet. Two satellites chase each other in orbit, and tiny changes in their separation reveal where gravity has strengthened or weakened. As ice melts and water shifts, gravity changes, and the satellites detect the redistribution with a precision that feels almost implausible. It is not a photograph of water, it is a measurement of weight. Grace cannot see every detail at the coast, but it closes the mass budget, and budgets are where uncertainty gets cornered. It tells us how much water is being added to the ocean from land ice and other sources, even when the ocean surface is rough. When combined with altimetry, it helps separate expansion from added mass, turning a single curve into two interpretable causes. The elegance is in the cross-check because independent measurements should agree if the physics is right. These systems are independent by design, and that independence is the point when the stakes are global. Floats measure temperature and salinity in the water column, where heat is stored and stratification forms. Altimeters measure the ocean surface height across basins, where expansion and circulation leave their imprint. Gravity missions measure mass changes that height alone cannot reveal, especially when ice sheets lose weight. When three different methods point in the same direction, the argument becomes less about belief and more about accounting. Ocean heat content is the ocean's memory of the energy imbalance, written into an enormous volume of moving water. Weather can shuffle heat between ocean and air, and that shuffle can dominate headlines for a season. Yet the integrated ocean trend persists, because the ocean is where most of the excess energy goes. When ocean heat content rises across datasets, the ledger is hard to dispute, even when surface temperatures pause or surge. The ocean is the long bookkeeper, and it does not forget quickly. The ocean does not warm like a pot on a stove, because mixing and circulation redistribute energy in 3 dimensions. Winds stir the surface and push water into gyres and boundary currents, creating convergent zones where heat can be driven downward. Overturning circulation moves heat into the interior on longer timescales, linking the surface to deep pathways that can take decades to centuries. In a cross-section view, warm colours sink along sloping density surfaces, sliding into darker layers. The result is uneven warming, with hotspots and shadows that shift over time. Natural variability still matters, and we name it without letting it dominate the story we can measure. El Niño and La Niña shift heat between ocean and atmosphere, changing global surface temperature temporarily and reshaping rainfall patterns. During El Niño, warm water spreads across the tropical Pacific, and the atmosphere responds as if a heater has been moved. During La Niña, heat is pushed back into the western Pacific and deeper layers, and the surface can cool while the system keeps gaining energy. They change the distribution of heat, not the long-term direction of the energy gain. Volcanoes also leave fingerprints that help test the physics, because they inject a known disturbance into the system. Stratospheric aerosols reflect sunlight and cool the surface for a year or two, dimming the planet like a thin veil. In satellite imagery, the plume spreads into a pale ring around the globe, and sunlight weakens at the surface. After the aerosols fade, the underlying ocean heat trend resumes because the forcing persists and the imbalance returns. These events are like controlled experiments we did not ask for, and they still teach. Now we connect heat to sea level, because the ocean translates energy into geometry, and geometry is visible. Global mean sea level is rising, and the curve shows acceleration in the satellite era, bending upward rather than climbing at a steady rate. That rise is a composite of expansion and added water, and the proportions shift with time. The ocean surface is not a rigid plane, it is a dynamic boundary that responds to heat, mass, and motion. Thermal expansion is the first component, and it is conceptually simple even when the patterns are complex. Warmer water occupies more volume, so the same mass takes more space, and the sea surface lifts as a result. Expansion depends on temperature and pressure, so the pattern varies by depth and region, with different sensitivities in different water masses. In warm tropical waters, expansion per degree can be larger than in cold polar waters, and that matters for regional sea level. The steric signal is also layered, because the surface warms first while deeper layers respond more slowly. The second component is land ice melt, which adds mass to the ocean, and mass changes the baseline everywhere. Mountain glaciers retreat across many regions, and their meltwater flows to the sea through rivers that swell seasonally. Old photographs show glacier fronts once filling valleys, now replaced by bare rock and milky meltwater lakes. This contribution is measurable in glacier mass balance studies and in grace signals, and it is also visible in the geography of loss. Glaciers respond quickly compared to ice sheets, so they often lead the mass signal in the early stages of warming. Greenland is a larger reservoir, and its losses matter at global scale because the volume of stored ice is vast. Surface melt increases during warm seasons, and meltwater can reach the bed through cracks and moulins, lubricating the interface and speeding ice flow. On aerial footage, blue melt ponds appear on white ice like scattered glass, then drain suddenly into darkness. Outlet glaciers can thin and retreat, adding ice to the ocean as discharge, and their grounding lines can migrate inland. The system is both thermodynamic and mechanical, and both pathways are observed. Antarctica adds a different kind of risk because of its geometry and ocean exposure, not because it melts like a simple block. Warm water can intrude onto continental shelves and melt ice shelves from below, carving cavities where ice meets sea. When shelves thin, they buttress grounded ice less effectively, and flow to the sea can accelerate, sometimes abruptly. In radar imagery, fractures lengthen like drawn lines, and calving fronts break into tabular icebergs that drift away. The key vulnerability is not the floating ice itself, but what it restrains behind it. We avoid exaggeration by staying with what is observed and what is physically constrained, even when the visuals feel dramatic. Ice sheets respond over years to centuries, and their dynamics are complex, involving bed topography, friction, and ocean heat delivery. Yet the direction of mass change is measurable, and it aligns with sea level budgets across independent methods. The uncertainty is in pace and regional detail, not in whether mass is being lost. That distinction matters because it separates honest caution from manufactured doubt. Sea level rise is not uniform, and local experience can diverge sharply from the global mean, sometimes by a factor of 2. Ocean currents pile water up in some regions and draw it down in others, shaping sea level like a landscape. Winds can push surface water toward coasts, raising levels seasonally or persistently, and the effect can linger when patterns lock in. In maps, bands of higher sea level appear as warm colours, tracing the paths of trade winds and gyres. The ocean's surface is a dynamic topography, and coastlines sit on its edge. Atmospheric pressure also matters through the inverted barometer effect, a subtle mechanism with real consequences during extremes. Lower pressure allows the sea surface to rise slightly, while higher pressure depresses it, because the ocean responds like a flexible membrane. These effects are small but important when combined with storms, tides, and already elevated baseline sea level. A storm surge is not just wind-driven water, it is also the atmosphere's weight changing over hours. When the baseline creeps upward, the same storm can cross a threshold that used to hold, land itself moves, and tide gauges measure the relative result, which can confuse the story if we ignore the ground. Subsidence from groundwater pumping, sediment compaction, and tectonics can amplify local rise, turning a global trend into a local emergency. Uplift from tectonics or post-glacial rebound can offset it, at least temporarily, making some places appear safer than the global mean suggests. In time-lapse visuals, a city sinks millimetre by millimetre, invisible until the water arrives. Relative sea level is what people experience, and it is a sum of ocean and land. There is also a gravitational and rotational fingerprint to melting ice, and it can feel counterintuitive at first. Large ice sheets attract ocean water gravitationally, so nearby sea level can fall as ice mass shrinks and the pull weakens. Farther away, sea level can rise more than the global mean, reshaping regional risk in patterns that follow physics, not politics. Earth's rotation also adjusts as mass redistributes, subtly changing the shape of the ocean surface. The planet responds as a connected system, and the shoreline inherits that complexity. So when we say sea level is rising, we mean two things at once, and both are true in different frames. The global mean is a planetary metric tied to heat and mass budgets, a number that belongs to the whole Earth. The local shoreline is a moving target shaped by currents, winds, gravity, and land motion, and it decides where floods occur. One curve can describe the planet, while another describes a neighbourhood street. The mystery is that both curves are real, and they can diverge. The ocean's warming also reshapes circulation, and that reshaping can be quiet at first, almost invisible in daily life. Density depends on temperature and salinity, and density gradients drive currents, from surface flows to deep pathways. Add heat and fresh water, and the gradients shift, altering pathways of heat and nutrients, sometimes in ways that only appear in long records. In a layered animation, isopycnals tilt and slide, and currents adjust their routes like rivers finding new channels. Circulation is the ocean's internal architecture, and warming can bend its beams. In the Atlantic, scientists watch the overturning circulation because it moves heat northward and helps set regional climates. Observations suggest variability and possible long-term change, though uncertainties remain, especially in separating trend from multi-decadal swings. The key is that the mechanism is sensitive to warming and freshwater input, which can reduce surface density and hinder sinking. Instruments moored across latitudes measure currents day after day, turning motion into numbers. The question is not whether the ocean moves, it is how its balance shifts when density changes. Currents also influence regional sea level by changing how water is stored in basins, like wind-driven piles in a tilted bowl. A strengthened trade wind pattern can raise sea level in the Western Pacific, while lowering it in the east, even as the global mean rises. A shift in boundary currents can change coastal sea level along continents, affecting ports and wetlands that depend on narrow margins. In coastal footage, a high tide reaches farther onto a seawall than it used to, not because of one cause, but because several align. Regional sea level is where circulation becomes personal. Warming increases the odds of marine heat waves, which are extreme events in the ocean's temperature field that can arrive like silent weather. They are defined by thresholds relative to local climatology and by duration, not just peak temperature, because ecosystems feel persistence. A few degrees for weeks can be ecologically decisive, even if the water still feels cool to a human hand. On thermal maps, a heat wave blooms as a red stain across the sea, lingering instead of passing. The ocean can hold an anomaly in place, and life must endure it. Marine heat waves can be driven by persistent atmospheric patterns that reduce the ocean's usual defenses against warming. Clear skies increase solar heating, and weak winds reduce mixing that would bring cooler water up from below. Currents can also advect warm water into regions that are not adapted to it, turning a familiar habitat into a thermal trap. Sometimes the heat wave is not a single cause, but a coincidence of calm air, bright sun, and altered flow. The unsettling part is how ordinary the ingredients are, and how extraordinary the outcome becomes. Coral bleaching is one of the clearest biological responses to repeated heat stress, and it is visible even from the air. Corals live near thermal limits in many tropical regions, and small anomalies can push them over thresholds that have been stable for centuries. When heat persists, corals expel symbiotic algae, losing colour and a major source of energy, and the reef turns pale like bone. Underwater, fish move through a landscape that looks drained of life, even when the structure remains. The reef does not vanish in a day, but its function can. Bleaching is not always immediate death, but recovery takes time and stable conditions, which are becoming harder to guarantee. If heat waves recur too frequently, ecosystems cannot rebuild between events, and the interval that once allowed regrowth collapses. The result can be a shift from coral-dominated reefs to algae-dominated systems, changing habitat complexity and the communities it supports. A reef is not just coral, it is a city of niches, and bleaching is a citywide power loss. The question becomes uncomfortable. How often can a system be shocked before it reorganizes? The key point is pacing, not drama, because pacing determines whether resilience has room to operate. A single heat wave can be survived, depending on intensity and duration, and depending on what came before it. Repeated heat stress compresses recovery windows, and that compression changes long-term ecosystem trajectories even without a single catastrophic moment. The ocean can change by accumulation, not by spectacle, and that is part of its mystery. What looks like stability can be a system running out of time. Warming also changes oxygen, and the mechanism is basic chemistry and physics, even if the outcomes are complex. Warmer water holds less dissolved oxygen at equilibrium because gas solubility declines as temperature rises. At the same time, stronger stratification reduces mixing that would ventilate deeper layers, limiting resupply from the surface. Oxygen is not just a number, it is a constraint on metabolism, movement, and survival. When oxygen declines, the ocean's living space can shrink. Stratification increases when the surface warms and freshens relative to deeper water, creating a lighter layer that resists sinking. A lighter surface layer acts like a lid, and the ocean becomes more layered, with fewer opportunities for deep ventilation. That layering can trap heat near the surface while starving the interior of oxygen, and it can also alter nutrient transport. In a simple visual, the surface becomes a bright, warm sheet, and the darker water below grows more isolated. The ocean still moves, but the exchange weakens. Deoxygenation is not uniform, and it interacts with biology and circulation, producing regional patterns that matter for fisheries, In some regions, nutrient runoff and warming can intensify coastal hypoxia, creating seasonal dead zones where oxygen drops too low for many species. In the open ocean, expanding oxygen minimum zones can compress habitat for fish and other species, forcing them into thinner layers. That compression can increase predator-prey encounters and change migration routes, which scientists can detect in catch records and tagging studies. The ocean's chemistry becomes a map of constraints. Low oxygen changes food webs and fisheries, because many species have narrow oxygen tolerances and limited flexibility. Fish may move to cooler or more oxygenated waters, shifting catch locations and management boundaries, and sometimes moving across national lines. These are measurable changes that ripple through economies, from small boats to global markets, even when the water looks the same. A port can remain in place while the resource moves away, and that mismatch creates tension. The ocean's changes are not only physical, they are logistical and political. Oxygen also matters for carbon cycling, because it shapes how organic matter is decomposed as it sinks and is consumed. In low oxygen waters, different microbial pathways dominate, producing different byproducts and altering nutrient regeneration. That can affect nutrient availability and greenhouse gas production in some settings, especially where oxygen becomes very low. The chemistry of decay changes when oxygen is scarce, and the ocean's internal recycling shifts with it. Even in darkness, the ocean is busy, and its microbes respond to the new baseline. The ocean's carbon uptake is another quiet integrator that links chemistry to heat, and it is one reason warming is not the only stressor. The ocean absorbs a large fraction of human CO2 emissions, slowing atmospheric rise, and that service comes with a cost. That uptake alters seawater chemistry and contributes to acidification, stressing calcifying organisms that build shells and skeletons. In close-up imagery, tiny pteropods and corals become symbols of a chemical shift, not because they are the only victims, but because they are sensitive. The ocean buffers the air and the ocean pays. Warming and stratification can influence how efficiently carbon is stored, because storage depends on moving carbon away from the surface. If surface waters mix less with depth, less carbon may be transported into the interior, and more may remain near the surface where it can exchange back. The details vary by region, but the coupling is physically unavoidable, linking heat, layering, and carbon pathways. The ocean's memory is not only thermal, it is chemical, and it accumulates quietly. At this point, the ocean stops being a backdrop and becomes a witness, recording the imbalance in multiple languages at once. It records the energy imbalance as heat content, and it expresses it as sea level rise, translating invisible joules into visible centimeters. It also translates warming into circulation shifts, ecological stress, and oxygen loss, changes that can be mapped, measured, and revisited. The same water that reflects the sky also stores the story beneath it. If the atmosphere is the headline, the ocean is the archive. We return again to the documentary's restraint, because the ocean invites both awe and exaggeration, and both can distort judgment. The measurements have gaps, and the uncertainties are real, especially in the deep ocean and polar regions where sampling is hardest. Yet the direction of change is consistent across independent observing systems, and consistency is the hallmark of a robust signal. The mystery is not whether the ocean is changing, but how its many layers will respond together. What we do not know is bounded by what we do know. The ocean's memory is also a warning about lag, because water holds heat and releases it slowly, even when the surface seems calm. Heat stored today can influence sea level and climate for decades, even if forcing stabilizes, because expansion and circulation do not stop on command. That lag is not a prophecy. It is inertia built into water's heat capacity and circulation timescales, and it is measurable in the slow penetration of warming. The ocean is not quick to forget, and it is not quick to cool. So the story is not that the ocean suddenly changed, but that it is steadily integrating a new baseline, one measurement cycle at a time. The sea surface rises by millimeters, then centimeters, then more, and the curve keeps climbing even when the climb is hard to feel. The heat content rises in joules so large they are hard to visualize, yet they are measured, cross-checked, and repeated. In a graphic, the numbers grow until they stop feeling like weather and start feeling like geology. The ocean makes time visible by accumulating change. The mystery is that the most consequential changes can be the least visible, hiding inside averages and slow trends. A slightly higher sea level turns storm surge into a different event, pushing water over thresholds that used to hold. A slightly warmer ocean turns a seasonal stress into a recurring heat wave, and recurrence is what breaks recovery. We are used to watching for sudden disasters, yet the ocean often changes by persistence. What does it mean when the background becomes the driver? As oceans rise and warm, the cryosphere begins to change in ways that amplify the signal. Ice and snow are the planet's reflective shield, and their loss darkens Earth's surface, allowing more sunlight to be absorbed. Next, we follow that bright boundary as it retreats, and we measure what it releases. As oceans rise and warm, the cryosphere begins to change in ways that amplify the signal. Ice and snow are not only water stored on land, waiting quietly in frozen reservoirs. They are also a reflective skin, thin in places, immense in others, that helps regulate how much sunlight Earth keeps. From orbit, the cryosphere looks like a bright boundary between energy absorbed and energy returned. It is a world of whites and pale blues, stitched to darker seas and rock like a torn seam. That brightness is albedo, a measure of reflectivity that functions like a planetary thermostat. In plain terms, it decides whether sunlight is bounced away or kept as heat. When sunlight hits fresh snow, much of it is reflected back to space in the visible spectrum. Snow crystals scatter light efficiently because of their structure and the air trapped between grains. When sunlight hits open ocean or dark rock, much more is absorbed and converted into heat. The difference is not subtle. Bright snow can reflect most incoming light, while open water can swallow it. This is a feedback, not a conspiracy, and it does not require anyone to coordinate it. Retreating ice exposes darker surfaces that absorb more energy, which warms the region and drives more melt. The physics is automatic and it runs even when no one is watching. The feedback is strongest where ice loss is rapid and sunlight is available, especially under clear summer skies. It is also seasonal, because the timing of melt can lengthen the period of dark exposure. If snow disappears weeks earlier, the surface spends extra time absorbing sunlight during the brightest part of the year. That extra energy does not vanish at sunset, because the ocean and ground store heat and release it slowly. The result is a longer, warmer tail to the melt season. We can measure albedo change directly with satellites that track reflected shortwave radiation. Instruments convert brightness into energy terms, mapping how much sunlight is reflected across the planet each day. We can also infer it from the visible retreat of snow lines, sea ice edges, and glacier fronts. The central question stays the same, even as the images grow more dramatic. What is changing now? How do we separate cycles from forcing? And what do the best observations say without exaggeration? This question has a history, because people have measured ice long before satellites existed. Early glaciologists sketched glacier tongues and marked boulders at the ice edge, returning years later to see what moved. In the 20th century, aerial photographs began to reveal retreat in a way the eye could not deny. Now the record is global, continuous and numerical, yet it still points back to the same story. Ice loss is not one phenomenon because the cryosphere is built from different kinds of ice. Mountain glaciers are small compared to ice sheets, but they respond quickly to warming. Ice sheets are vast and slow, yet they can accelerate through mechanical instabilities. The physics is shared, but the timescales and failure points differ, and that difference shapes what sea level sees first. Start with glaciers, because they behave like sensitive thermometers in the landscape. They cling to valleys and high basins, where snowfall once outpaced summer melt. A glacier's mass balance is the difference between snowfall gained and melt lost over a year. When summer's warm or winter's dry, the balance shifts negative and the glacier thins. Thinning lowers the surface into warmer air, which increases melt and pushes the system further out of balance. This is not just temperature, but energy. Sunlight, warm winds, and humidity all matter. The melt season can also lengthen, turning what used to be brief summer loss into a prolonged drain. In many regions, the snowline climbs higher, shrinking the area where snow can accumulate and survive. Glacier retreat is measured with field stakes, airborne laser altimetry, and repeat satellite elevation maps. Stakes drilled into ice record how much surface is lost centimetre by centimetre through the season. Aircraft and satellites then scale that local truth into regional maps of thinning. The signal is coherent across many regions, even though local weather still matters and can briefly mask the trend. Some glaciers surge or pause for internal reasons, and that variability is real. A surge can push ice forward even during a warming period because it is driven by internal plumbing and stress. Yet the net trend across inventories is persistent mass loss, consistent with a warming energy budget. When the accounting is done across thousands of glaciers, the noise averages out and the direction remains. Glaciers also matter because they connect heat to sea level quickly. Their meltwater reaches the ocean without needing complex ice shelf dynamics or deep grounding lines. Their contribution is limited by their total volume, but it arrives early in the timeline. In a warming world, glaciers are often the first cryosphere reservoir to cash out, turning stored ice into immediate rise. Ice sheets are different because they are not just piles of snow and ice. They are flowing systems with grounded interiors and floating margins, moving under their own weight like slow rivers. Their stability depends on bed topography, friction at the base, and the geometry of their contact with the ocean. This is where acceleration becomes less intuitive, and where measurements have to be paired with mechanics. An ice sheet loses mass in two main ways. It can melt at the surface and send water away as runoff, sometimes refreezing in layers before escaping. It can also discharge ice into the ocean through fast outlet glaciers that carve or melt at their fronts. The balance between these pathways varies by region and by year, and that variability is itself a clue. That variation is measurable with gravity missions, altimetry, and ice velocity maps. Gravity satellites sense mass loss as tiny changes in Earth's gravitational field, a planetary scale weigh-in. Altimeters measure surface height, detecting thinning even where no one can safely travel. Velocity maps track the motion of ice by comparing repeated images, revealing where flow speeds up like a tightening current. A key concept is buttressing, because floating ice shelves can restrain grounded ice upstream. Ice shelves are already floating, so their melting does not directly raise sea level. Their importance is mechanical, because they act like braces that slow the flow of grounded ice behind them. They grip pinning points and sidewalls, and that friction is a kind of invisible architecture. When shelves thin or fracture, resistance drops and upstream ice can speed up. Cracks can lengthen into rifts, and rifts can unzip into calving events that remove huge plates of ice. In satellite imagery, the surface can look calm, almost polished, until a fracture line appears like a dark scar. The mystery is that the most consequential change can be a loss of resistance, not a dramatic melt pond. Another key concept is the grounding line, where ice transitions from grounded to floating. Grounding lines can migrate inland when the ocean melts ice at the base, or when thinning reduces contact with the bed. If the bed slopes downward inland, retreat can expose thicker ice to flotation. That geometry can create a self-reinforcing retreat in some settings, because each step inland makes the next step easier. Basal lubrication adds another pathway for speed up, especially where surface melt reaches the bed. Water at the base can reduce friction and allow ice to slide faster, like a heavy object on a thin film. The effect can be transient if drainage channels evolve and pressure drops, yet repeated melt seasons can still alter the basal system and change long-term flow, reshaping how the ice sheet couples to the rock below. Greenland is the clearest place to see surface melt acting at scale. In warm summers, melt spreads across the ice sheet surface, forming streams and lakes that glitter like broken mirrors. The water is not just a surface feature, but an energy signal. Liquid water means the surface has reached melting conditions. As melt expands upward in elevation, it reaches areas once protected by persistent cold. Some lakes drain suddenly through fractures and moulins, delivering water to depth in hours. The surface can collapse into a whirlpool, and the lake that looked permanent one day can vanish the next. That water can briefly speed outlet glaciers, and it can also warm the ice internally. Even small temperature changes matter in ice, because viscosity is sensitive to heat and stress. Greenland's mass loss is measured in multiple ways that cross-check each other. GRACE detects the loss of mass as a change in gravity, integrating the entire ice sheet into a single measurable signal. Altimetry detects thinning and surface lowering, tracing where the ice is losing height year by year. Feature tracking and radar interferometry detect changes in ice velocity along outlet glaciers, showing where flow accelerates toward the coast. The agreement across methods is the kind of coherence the documentary keeps returning to. When independent tools, gravity, height, and motion, tell the same story, uncertainty narrows even if it never disappears. The measurements do not need drama to be persuasive because they are consistent. The ice sheet is losing mass, and it is doing so through both melt and discharge. Greenland's melt is not uniform, and extreme years often involve specific atmospheric patterns. Blocking highs can park warm, clear air over the ice, increasing sunlight and reducing cooling clouds. Under these domes of stagnant air, the surface receives more direct radiation, and winds can bring warmth from lower latitudes. The sky becomes part of the mechanism, not just the backdrop. Atmospheric rivers can deliver pulses of heat and moisture that raise melt and rainfall. These narrow corridors of water vapor carry latent heat, releasing it when moisture condenses and falls. When rain falls on snow or bare ice, it delivers heat efficiently and can trigger rapid runoff. Rain also darkens the surface and can strip away fresh snow, exposing older, darker layers beneath. These patterns also help separate weather from climate in the public mind. A single blocking event is weather, and Greenland has always had variability across decades. The unusual signal is the frequency and intensity of melt-favourable conditions in a warmer background. The baseline shift loads the dice, so the same circulation pattern produces more melt than it used to. Greenland also shows how albedo feedback works at the surface. As melt begins, snow grains grow and reflect less light, because larger grains scatter less efficiently. As bare ice is exposed, darker impurities and meltwater films can reduce reflectivity further. Dust, soot, and biological material can concentrate on the surface as melt removes clean snow, leaving behind a darker skin. The surface absorbs more sunlight, which increases melt, which exposes more dark ice. The feedback is local, measurable, and physical, and it can be mapped in time-lapse from space. In imagery, the bright interior can develop grey-blue patches that spread like bruises across the summer surface. The question becomes unsettlingly simple. How much extra energy is being absorbed, and where does it go next? Yet Greenland is not only a surface story, because the ocean matters at the margins. Warm water can undercut marine terminating glaciers, thinning them at the front and encouraging retreat. The ice face can become unstable, calving more frequently as it loses support from below. Retreat can reduce backstress and increase flow from inland, drawing down ice like a siphon. The result is a coupled system where air and ocean both push on the same boundary. Surface melt can weaken ice, while ocean heat attacks the front, and the glacier responds by accelerating. This coupling is why simple temperature averages are not enough to explain what we see. The ice sheet is responding to a changing energy environment from multiple directions. Antarctica is the other pole of the mystery, because its dominant vulnerabilities are different. Much of Antarctica is cold enough that surface melt is limited compared to Greenland, at least for now. The critical action often happens where ocean water meets ice shelves from below. That makes Antarctica a story about ocean heat delivery and ice shelf integrity, told in darkness under the floating margins. West Antarctica is especially vulnerable because much of its ice rests on bedrock below sea level. That geometry allows warm water to access grounding zones through deep channels carved into the continental shelf. When ice shelves thin, buttressing weakens and grounded ice can accelerate toward the sea. The risk is not that Antarctica melts like an ice cube. The risk is that its flow regime can shift and then keep shifting. A major player is warm circumpolar deep water, which can intrude onto continental shelves. Driven by winds and ocean circulation, it can rise and spill into the cavities beneath ice shelves. When it reaches ice shelf cavities, it melts ice from below and thins the shelf. This melting can be focused along channels, carving the underside into shapes that satellites cannot see directly. Thinning reduces contact with pinning points and weakens the shelf's ability to resist flow. Once a shelf loses its grip, the upstream glaciers can respond quickly, accelerating like traffic when a bottleneck clears. This is measurable through ocean moorings, ship surveys, and satellite-based thickness change. Even when the surface looks unchanged, the underside can be eroding, quietly removing the structure that provides restraint. Antarctic change is not uniform, and that is often used to confuse the narrative. Some regions gain snowfall in some years because warmer air can hold more moisture and deliver heavier precipitation. Snowfall can offset losses locally and temporarily, and that is part of honest accounting. The key question is whether gains can counter the dynamic losses where the system is most sensitive, especially near vulnerable grounding lines. East Antarctica is often described as a stabilizing counterweight, but that framing is too simple. East Antarctica holds the largest ice volume, and much of it is high and cold, insulated from short-term warmth. Yet parts of its margin include marine-based basins and vulnerable outlet glaciers. Stability in the interior does not guarantee stability at the edges, where ocean access and geometry can matter more than air temperature. We also have to separate short-term surface mass balance from long-term sea level commitment. A snowy year can look like recovery in a single metric, while discharge continues at the coast, and thinning persists in key outlets. The ice sheet's response integrates over time, and its geometry can lock in future loss. The documentary's restraint matters here, because the uncertainty is real, but it is bounded by physics and by what has already changed. Sea level commitment is the long shadow of cryosphere change. When an ice sheet thins and grounding lines retreat, some changes are difficult to reverse quickly, even if conditions later improve. Even if warming stabilized, the ocean would remain warm for decades, continuing to erode ice shelves. The system can keep moving toward a new configuration long after the initial push, because inertia is built into both ice flow and ocean heat. This is where the timescales become unsettling, because they stretch beyond a news cycle. Ice sheets respond over years, decades, and centuries depending on the process and the region. Surface melt can change quickly, and discharge can accelerate within years. Full equilibration of an ice sheet to a new climate can take far longer, and the lag can hide the future in the present. The albedo feedback ties these timescales back to the energy budget. Losing reflective area increases absorbed sunlight, especially in polar regions with long, summer days and low sun angles. That extra absorption warms the ocean surface and the lower atmosphere, building heat where ice is already stressed. Warmer water then attacks ice shelves and glacier fronts, linking albedo change to dynamic loss in a loop that spans air, ocean, and ice. Sea ice adds another layer because it is thin, mobile, and highly reflective. It forms and breaks with winds and currents, opening leads that flash dark water between bright plates. When sea ice retreats, the ocean absorbs more sunlight in summer and releases more heat in fall and winter. That heat can delay freeze up and thin the next season's ice, making the system easier to disturb again. The feedback is rapid, and it reshapes polar amplification even where land ice is not directly involved. A warmer Arctic Ocean can influence the temperature and moisture of air masses moving over nearby land, nudging the broader cryosphere. The changes are visible in satellite mosaics, where late summer ice looks fractured and sparse rather than solid. The question becomes not whether sea ice varies, but how its baseline is shifting. We keep the central question in view by asking what is measured, not what is imagined. Satellite records show declining Arctic sea ice extent and thickness over recent decades. Field campaigns and buoys confirm thinning and changes in ice age distribution, with less multi-year ice surviving summer. The Antarctic sea ice story is more variable, but recent sharp declines highlight sensitivity to winds and ocean heat, and they remind us that variability does not mean immunity. The cryosphere also interacts with the ocean's rise in a second way, through freshwater. Meltwater freshens surface layers, increasing stratification and reducing vertical mixing. Reduced mixing can trap heat near the surface in some regions, while also limiting oxygen ventilation in deeper waters. Freshwater can also influence circulation patterns that redistribute heat toward ice margins, changing where the ocean delivers its energy. None of these mechanisms require a single dramatic threshold to matter. Acceleration can come from feedbacks that compound small changes, and from geometry that turns retreat into a one-way slope. It can also come from coincidence, when warm air, warm water, and weak buttressing align in the same place and season. The mystery is not that ice melts. The mystery is how quickly the system can reorganize once key supports weaken, and how quietly that reorganization can begin. We also avoid the opposite error, which is to treat every crack as immediate collapse. Ice shelves carve naturally, and glaciers have always advanced and retreated with shifting weather and ocean conditions. The difference now is the coherence across regions and the direction of the mass budget. When gravity, height, and flow all point to loss, the signal is not a camera trick, it is a convergence. So Chapter 4 is a story of bright surfaces turning dark, and of slow reservoirs finding faster pathways to the sea. It is a story of different ice responding to the same energy imbalance through different mechanics, sometimes subtle until they suddenly are not. It is also a story of commitment, because the ocean and ice remember heat for a long time. The baseline shifts quietly, and the cryosphere answers with motion, measured, mapped, and increasingly difficult to dismiss. Now the narrative pivots from frozen boundaries to the air that delivers heat and moisture. With more energy in the system, the atmosphere's behaviour changes in ways we can measure. Storms, droughts, and extremes become the next chapter of the mystery. Now the narrative pivots from frozen boundaries to the air that delivers heat and moisture. The atmosphere looks chaotic from the ground, yet it follows rules that can be measured and tested. In time-lapse, cloud streets braid across oceans, thunderstorms pulse like living cells, and dust plumes unfurl, each motion tracing invisible gradients of energy. Weather is motion powered by energy gradients, and warming changes those gradients everywhere. Add heat to air and ocean, and you do not get one outcome. You get a wider menu of extremes shaped by moisture, circulation, and land feedbacks. The same added energy can amplify floods in one season, deepen drought in the next, and sharpen heat in between, because the system is coupled, not linear. Start with a basic constraint that hides inside every storm. Warmer air can hold more water vapor before it condenses into cloud and rain. This is thermodynamics, not a forecast, and it sets an upper bound. Think of the atmosphere as a moving reservoir whose capacity expands as temperature rises, even before winds and clouds decide where the water goes. In plain language, each degree Celsius of warming allows about 7% more water vapor. That relationship is called Clausius, Clapeyron, and it is a first-order scaling. It does not guarantee heavier rain every day, but it loads the atmosphere with more fuel. In a visual sense, the air becomes a thicker sponge, able to carry more moisture between ocean evaporation and storm release. The reason is molecular and exacting. Warmer temperatures increase the saturation vapor pressure, which is the maximum water vapor air can hold at equilibrium. Because that curve rises steeply with temperature, small warming produces a noticeable jump in potential moisture. The math is old, rooted in 19th century physics, yet its consequences are newly visible in a warming world. Water vapor is also a greenhouse gas, so it amplifies warming that CO2 started. The atmosphere responds quickly because water vapor cycles in days. CO2 persists for decades to centuries, so it sets the long-lived push. This pairing matters. Carbon dioxide is the slow lever, while water vapor is the fast echo that follows temperature upward. When moist air rises and cools, vapor condenses and releases latent heat. That released heat strengthens updrafts and can intensify storms. The same physics that makes clouds also makes extremes more likely. In radar imagery, you can almost see the engine. Rising columns brighten, ice forms aloft, and the storm's core hardens as latent heat feeds vertical motion. Latent heat is not a metaphor, and it is not small. It is energy stored in phase change, released when vapor becomes liquid or ice. That release can lower pressure locally, draw in more air, and help storms organize. In some systems, it can also alter the larger circulation around the storm, subtly steering where the heaviest rain falls. This is why downpours can intensify even where average rainfall declines. A region can have fewer rain days, yet stronger rain when it arrives. The water cycle can become more intermittent, with longer dry spells punctuated by heavier bursts. The paradox is only apparent. Less frequent storms can still be wetter storms, because the atmosphere arrives preloaded. The timing matters as much as the total. When rain comes in short, intense bursts, more water runs off instead of soaking in. Streams rise faster, drainage systems are overwhelmed, and soils can seal at the surface. Then, after the flood pulse passes, the ground may still be thirsty, because infiltration did not keep pace with intensity. Observations support this pattern in many places, though not uniformly everywhere. Rain gauges show increases in heavy precipitation in multiple regions. Satellites and reanalysis add spatial coverage, but they carry their own uncertainties. Gauges can miss wind-driven rain, and sparse networks leave gaps, while satellites infer rainfall from cloud properties that must be calibrated against the ground. Even the definition of heavy is local. Scientists often use percentiles, like the top 1% of daily totals, so deserts and rainforests can be compared fairly. They also track short-duration extremes, because a 1-hour deluge can do more damage than a gentle day-long rain. The story of extremes is increasingly told at finer timescales, where infrastructure and safety are tested. Attribution science asks a disciplined question about these changes. Did human-caused warming make a given event more likely or more intense? The answer is probabilistic, and it depends on the event type and data quality. It is less a courtroom verdict than a quantified shift in odds, expressed with confidence intervals and careful language. Scientists compare the world as observed with a counterfactual world without added greenhouse gases. Models are used as controlled experiments, but they are tested against observations. Uncertainty is reported because confidence varies by region and mechanism. In practice, researchers run large ensembles, many simulated worlds, so rare events can be sampled enough to estimate change probability. For heavy rainfall, the physical expectation is strong because moisture capacity is well understood. For specific storm tracks and local totals, confidence can drop because circulation noise is large. The key is separating thermodynamic certainty from dynamic complexity. In other words, we know the air can carry more water, yet we cannot always predict where the atmosphere will choose to unload it. There is also the question of scale. A hurricane's rainfall can be intensified by warmer air and warmer ocean surfaces, while its path may still depend on steering winds and chance. A stalled frontal boundary can turn into a flood when moisture transport is high. Even if the front itself is not caused by warming, attribution often finds the fingerprint in intensity rather than in the existence of the weather pattern. Heat extremes are the other side of the same energy shift. When the baseline warms, the entire distribution of temperatures moves. That shift alone increases records, even if variability stayed the same. On a graph, the bell curve slides to the right, and what used to be rare becomes merely uncommon. Variability still matters, because weather swings can widen or narrow from year to year. Yet a warmer mean makes the old extremes more common. It also makes new extremes possible, because thresholds get crossed more often. A heat wave that once required an unlikely alignment of conditions can become achievable under more ordinary circulation. A useful framing is the loaded dice, but we keep it quantitative. A small mean shift can multiply the odds of rare heat. The tail of the distribution is where risk grows fastest. When the tail thickens, the consequences are not abstract. Power grids strain, crops fail at flowering, and bodies lose their ability to cool. Heat is measured with thermometers, but also with reanalysis that blends instruments with physics. Heat waves are defined by duration and local thresholds, not just a single hot afternoon. The signal is clearer when we look across many stations and decades. Long records matter, because a few extraordinary summers can mislead if they are not placed in a century-scale context. Historically, heat records were kept for navigation, agriculture, and public health, long before climate change became a phrase. Today, those same station logs, handwritten ledgers turned into digital archives, help reveal the baseline shift. Yet measurement is never perfect, because instruments move, cities grow, and observing practices evolve. Homogenization methods try to correct these changes, making the long-term trend more trustworthy. Cities add a local amplifier called the urban heat island. Concrete and asphalt store heat and release it at night. Less vegetation means less evaporative cooling, so nights stay warmer. From above, thermal cameras show a mottled landscape, parks as cool islands, roadways as glowing ribbons, dense blocks radiating stored heat after sunset. This is not a global driver, but it is a human exposure multiplier. It changes who experiences dangerous heat first. It also complicates trend comparisons if station siting and land use change. A sensor that once sat in open ground may now be surrounded by development, and that local warming must be distinguished from the global signal. Heat risk is not only about air temperature. Humidity controls how well sweat evaporates, and evaporation is the body's main cooling pathway. When air is hot and humid, the body can lose its safety margin. The danger is quiet at first: fatigue, dizziness, a rising heart rate, until it becomes medical emergency. Wet bulb temperature captures that combined stress. It is the lowest temperature air can reach by evaporating water into it. As wet bulb rises, human cooling fails even in shade and with wind. This is why coastal and river basin heat can be uniquely oppressive, even when the thermometer reads similar values to a dry inland heat wave. There are physiological limits, and they are not negotiable. Sustained wet bulb near 35 degrees is often cited as a critical threshold for healthy humans. Real-world danger can occur lower, especially with sun, exertion, age, or illness. The body's cooling system is constrained by physics. When evaporation stalls, internal heat accumulates faster than it can be shed. Warming increases the probability of high wet bulb conditions in some regions. It does not mean those thresholds are reached everywhere, or often, yet. It means the envelope is expanding and the margin for error is shrinking. A night that used to bring relief may stay warm and damp, turning recovery into continued stress. Heat also reshapes drought because it increases atmospheric thirst. Even if rainfall stayed constant, warmer air can pull more moisture from soil and plants. This is evaporative demand, and it is a key bridge between heat and dryness. In practical terms, the same rain total can support less vegetation and less stream flow when the air's demand is higher. Evaporative demand is influenced by temperature, humidity, wind, and sunlight. Many drought indices incorporate these factors, translating weather into potential evaporation. When demand rises, soils dry faster between storms, and plants close stomata to conserve water. That conservatism can reduce growth and yield, even if rainfall statistics look unchanged. Drought is not one phenomenon, and definitions matter. Meteorological drought is low precipitation. Agricultural drought is soil moisture stress. Hydrological drought is low stream flow and depleted reservoirs. These categories can overlap, yet they can also unfold in sequence. First rain fails, then soils dry, then rivers and aquifers decline. Warming can worsen all three, but through different pathways. Higher evaporation can dry soils faster between rains. Earlier snowmelt can shift runoff earlier, leaving less water in late summer. In some regions, warming also changes the form of precipitation, turning snow into rain and reducing the slow-release storage that snowpack provides. Soil moisture feedbacks can lock drought in place. Dry soils reduce evaporation, which reduces local cooling. More energy goes into sensible heat, raising temperatures and increasing further drying. The land surface becomes a heat amplifier, and the boundary layer deepens, mixing warm, dry air downward and suppressing the conditions that might otherwise bring clouds. This feedback can intensify heat waves over land. It can also reduce cloud formation and rainfall in some settings. The land surface becomes an active participant, not just a passive boundary. A landscape that has dried out can change the day's weather, nudging the atmosphere toward clearer skies and higher afternoon temperatures. Snowpack is a seasonal reservoir, and its timing is a form of infrastructure. In many mountain regions, winter snow stores water until spring and summer melt. When warming turns snow to rain, storage shrinks. The visual shift is stark. A winter ridge that once held a bright, continuous mantle becomes patchy, with dark ground absorbing sunlight and accelerating melt. Earlier snowmelt shifts peak stream flow earlier in the year. That can increase spring flood risk while reducing warm season supply. The same basin can face both hazards depending on season. Water managers then confront a dilemma: release water to prevent floods or hold it back for summer, knowing the snow reservoir is less reliable. This matters for irrigation, hydropower, ecosystems, and wildfire. It also matters for water rights and planning that assume 20th century timing. The baseline shift turns old calendars into unreliable guides. In some places, the legal and engineering systems were built around normal melt dates that no longer arrive on schedule. Fire weather emerges from the coupling of heat, dryness, and wind. Hotter conditions dry fuels faster, from grasses to forests. Low humidity and strong winds then turn ignition into spread. On the ground, the change can be felt in texture: needles that snap instead of bend, leaf litter that crackles, and logs that lose their damp weight. Warming does not ignite fires by itself, and human land management still matters. Yet climate can set the background flammability and the length of fire season. In many regions, the window for large fires has widened. Earlier spring drying and later autumn rains can stretch the season at both ends, increasing the chance that ignition meets receptive fuels. Vapor pressure deficit is one metric that captures drying power. It increases with temperature, and it correlates with fuel moisture loss. Higher VPD can stress vegetation, increasing mortality and dead fuel. It also affects plant physiology directly, pulling water from leaves and raising the risk of hydraulic failure during prolonged heat. Drought can also invite insects and disease that weaken forests. Dead trees change fuel structure and continuity. The result is not a single cause, but a cascade that begins with heat and moisture imbalance. In aerial views, you can see the aftermath: patches of red and grey crowns, then a new pattern of burn severity when fire eventually arrives. Attribution for fire is complex because ignition sources and suppression policies vary. Scientists often attribute changes in fire weather indices more confidently than burned area. Burned area depends on people, terrain, and chance as well as climate. A lightning outbreak, a power line failure, or a single wind event can dominate outcomes, even under similar background dryness. Now we move upward, from surface feedbacks to the highways of the upper air. The jet stream helps steer storms and separate air masses. It is driven by temperature contrast between low and high latitudes. In satellite loops, it reveals itself indirectly. Storm tracks curving along its path, cloud bands stretching like brushstrokes across continents and oceans. Arctic amplification is observed, with the Arctic warming faster than the global average. Sea ice loss, albedo feedback, and heat transport all contribute. This reduces the pole to equator temperature gradient in the lower atmosphere. When bright ice retreats, darker ocean absorbs more sunlight, an energy shift that echoes through seasons, especially in autumn and early winter. The Arctic is not warming in isolation. Changes in sea ice alter heat and moisture fluxes from ocean to air, and they can influence the stability of the lower atmosphere. In some conditions, warmer Arctic air can reduce near-surface baroclinicity, which is one ingredient that helps energize mid-latitude storms. Yet the atmosphere is layered, and what happens near the surface does not always dictate what happens aloft. A weaker gradient can influence jet stream behavior, but the chain is not simple. The jet is also affected by stratospheric dynamics, tropical heating, and internal variability. Scientists debate how these influences combine. The debate persists because multiple mechanisms can push in different directions, and the observational record for some metrics is limited. One hypothesis is that reduced gradients can lead to a slower, wavier jet. A wavier jet can favour persistent patterns, including blocking highs and stalled lows. Persistence is what turns weather into prolonged extremes. When the atmosphere stops progressing, the same region can sit under the same air mass, day after day, until impacts accumulate. Blocking is a circulation pattern that resists movement for days to weeks. It can park heat domes, prolong drought, or stall rain-bearing systems. When storms stall, rainfall totals can accumulate into floods. The visuals are dramatic. A stationary low spins offshore, feeding moisture inland, while rivers rise beneath a sky that refuses to clear. Blocking has been recognized for decades, long before modern climate debates. Early meteorologists noticed stuck patterns that broke forecasts and prolonged impacts, and they developed indices to quantify them. Today, those same patterns are studied with reanalysis and satellite data, allowing researchers to compare events across continents and across time. What can be said confidently is narrower than what is often claimed. Arctic amplification is robustly observed. Some aspects of circulation variability and extremes show changes, but attribution is harder than for temperature. The atmosphere's dynamics contain large natural swings, and those swings can mask or mimic trends over short periods. Part of the difficulty is statistics, because the atmosphere is noisy. Jet stream patterns vary naturally across years and decades. Short records can mislead, and different metrics can give different answers. A trend can appear in one season and vanish in another, or it can depend on whether blocking is counted by geopotential height, wind reversal, or persistence thresholds. Models capture many large-scale features, but they differ in regional circulation responses. Resolution matters for blocking and storm tracks. Stratosphere representation matters for sudden warmings and polar vortex behavior. When the stratosphere is poorly resolved, the coupling between upper layers and surface weather can be misrepresented, which complicates conclusions about persistence. So the documentary stays disciplined about uncertainty. We can link warming to moisture increases and heat extremes with high confidence. We can link warming to some drought and fire weather changes with growing confidence, often region-specific. The strongest claims rest on mechanisms with clear physics and consistent observations, rather than on single dramatic events. For jet stream changes and blocking frequency, the evidence is mixed and still debated. Some studies find trends in certain seasons or regions. Others find variability dominates, or that signals depend on how blocking is defined. That tension is not failure. It is the scientific process working in public, with competing hypotheses tested against imperfect data. Yet even without a definitive jet trend, persistence can still increase impacts. A warmer atmosphere makes stalled patterns more damaging. The same stationary system can deliver heavier rain, higher heat, or faster drying than before. In that sense, thermodynamics can raise the stakes even when dynamics remain uncertain. This is the key synthesis of the chapter. Thermodynamics raises the ceiling on moisture and heat. Land feedbacks and circulation determine where that potential is realized. The question becomes less, will extremes happen, and more, where will the atmosphere choose to concentrate them, and for how long? We return to measurement because measurement is how mystery becomes legible. Extremes are tracked in station networks, satellites, and reanalysis. Event attribution combines those records with ensembles that estimate changed odds. Each dataset is a lens with its own distortions, so scientists compare lenses, looking for the consistent shape of the signal. The goal is not to claim every disaster is climate change. The goal is to quantify how the background has shifted and how that shift alters risk. Natural variability remains real, but it now rides on a rising baseline. When a rare event occurs, the relevant question is often how much extra heat or moisture the new baseline contributed, an increment that can be measured. The atmosphere is fast, but it is not separate from the rest of the system. It exchanges heat and moisture with land and ocean every day. It also carries chemistry that is changing, molecule by molecule. Under a microscope of spectroscopy, that chemistry is readable, absorption bands, scattering, and the subtle fingerprints that tell us what the air contains. Next, we follow that chemical shift and its ocean partnership. The atmosphere is only half the system, and the oceans are absorbing more than heat. The planet's composition is changing along with its energy balance. For most of human history, air chemistry felt fixed, like background noise that never changed its pitch. Now instruments show a fast, measurable shift in carbon moving through Earth's reservoirs, and the change is large enough to see in a single career. On a screen in a lab, the atmosphere becomes a trace, numbers stepping upward with each year. On a mountaintop, air is pulled through glass flasks and metal tubing, and the invisible becomes countable, repeatable, and hard to dismiss. Carbon is not only a climate driver that traps heat in infrared bands, carbon is also a chemical agent that changes water, soils, and biology molecule by molecule, and it does so whether we notice or not. When CO2 absorbs infrared radiation, it does not hold heat like a blanket in the casual sense. It changes how efficiently Earth can shed energy to space, altering the radiative balance and nudging the entire system toward a warmer equilibrium. But the chemistry story runs alongside the physics story, and it has its own rules. CO2 is reactive, and once it moves into water or living tissue, it participates in equilibria that can shift rapidly when concentrations rise. To separate natural cycles from human influence, we start with accounting. We ask where carbon goes, how long it stays, and what measurements confirm each step, because in a system this large, intuition is not enough. Earth's carbon cycle has two tempos that overlap but rarely confuse. There is a fast cycle linking air, life, and the surface ocean, and there is a slow cycle that stores carbon in places most people never see. In the fast cycle, plants pull CO2 from air through photosynthesis, then return it through respiration and decay. Chlorophyll captures photons, enzymes stitch carbon into sugars, and the carbon becomes wood, leaf, root, and seed. At night, and in winter, much of that carbon flows back out. Plant respiration continues, microbes digest litter and soil organic matter, and the atmosphere receives a steady exhale from the living land. Fires and microbes accelerate that return when conditions are hot and dry. A lightning strike can turn years of stored carbon into smoke in hours, while drought-stressed forests become more flammable and burn more completely. The surface ocean exchanges CO2 with the atmosphere in days to months. The exchange happens across a thin skin of water, where turbulence, bubbles, and wave breaking increase contact between air and sea. Winds, temperature, and mixing set how quickly the ocean takes up carbon. Cold water holds more dissolved gas, so high-latitude seas can absorb CO2 efficiently, until ice cover, stratification, or circulation changes limit that intake. This fast cycle creates the seasonal sawtooth in the Keeling curve. Northern land plants draw CO2 down in summer, then release it in winter, and the amplitude of that breathing has grown as ecosystems and agriculture have changed. Yet the fast cycle mostly rearranges carbon already near the surface. It does not explain the long-term rise because the rise persists through every season, like a staircase that keeps climbing, even as it oscillates. The slow cycle is Earth's deep storage and deep patience. Carbon is locked in rocks, deep ocean waters, and sediments for thousands to millions of years, and that storage is maintained by geology rather than biology. Weathering of silicate rocks consumes CO2 over long timescales, eventually storing carbon as dissolved ions. Rainwater becomes weak carbonic acid, it reacts with minerals, and the products are carried away in rivers as bicarbonate and other dissolved species. Rivers carry that chemistry to the sea, where carbonates can form. In shallow, warm waters, organisms and inorganic processes build calcium carbonate, and sediments accumulate, layer upon layer, turning chemistry into stone. Volcanoes and metamorphism return some carbon to the air, but slowly on human timescales. Subducted sediments are heated and transformed, CO2 is released, and over geologic time the planet vents that carbon back through arcs and rifts. The slow cycle usually balances itself over geologic time, not decades. It is a thermostat with a delayed response tuned to the pace of continents and oceans, not to the pace of engines and cities. Human emissions enter the fast cycle as a new, one-way injection from the slow reservoirs. Fossil fuels move ancient carbon into air in a geological instant, compressing millions of years of burial into a single century of combustion. Coal, oil, and gas are not just energy sources in this accounting. They are concentrated carbon that was removed from the surface system, and we are returning it at a rate the natural sinks did not evolve to match. Cement production adds another pulse by heating limestone and releasing CO2. In kilns, calcium carbonate is calcined into lime, and the carbon that once sat safely in rock is driven off as gas. Land clearing adds carbon by oxidizing biomass and weakening future uptake. When forests are cut or burned, carbon leaves trunks and soils, and the landscape often loses the capacity to pull as much CO2 back down. The key measurable fact is accumulation. About half of emitted CO2 stays in the atmosphere each year, while the rest enters land and ocean sinks, an average that hides a great deal of regional and seasonal complexity. That airborne fraction varies year to year, but the long-term rise remains. The atmosphere is the ledger we can measure directly, and it keeps gaining carbon, even when economies slow or weather patterns shift. We also measure fingerprints that separate sources without speculation. Atmospheric oxygen declines slightly as carbon is burned, and carbon isotopes shift toward fossil signatures, subtle changes that require careful calibration yet persist across networks. Fossil carbon is depleted in carbon-14 because it has decayed away over millions of years. It is also relatively depleted in carbon-13 compared with many natural sources, so the isotopic ratio in air drifts in a direction that matches combustion. Those fingerprints do not tell us everything about future change. They do tell us the added carbon is real, recent, and tied to combustion and land use, and that conclusion does not depend on any single model. Once CO2 enters the air, it does not behave like a simple pollutant that disappears quickly. Some is absorbed fast, but a significant fraction persists for centuries, because the deep ocean and rock weathering respond slowly. This persistence is why carbon is both a present forcing and a long commitment. The ocean's memory from earlier chapters applies to chemistry as well as heat, and that memory makes the future partly hostage to the past. A useful way to picture it is as a stack of timescales. Days to years move carbon between air, leaves, and the surface sea, while centuries to millennia govern how the deep ocean and sediments catch up. Now we follow the carbon into seawater, where the story changes character. Warming is one ocean stress, but acidification is a separate chemical shift, and it can unfold even when temperatures are stable. At the surface, the ocean looks constant, blue, reflective, and immense. Yet in a beaker, seawater reveals itself as a solution with balances and thresholds, and CO2 is a lever that can move those balances. When CO2 dissolves in seawater, it reacts with water to form carbonic acid. Carbonic acid partly dissociates, producing bicarbonate and hydrogen ions, and the reactions proceed toward equilibrium depending on temperature and existing chemistry. More hydrogen ions lower pH, which is the definition of acidification. The ocean remains alkaline overall, yet the direction of change is toward higher acidity, and the shift is measurable as a decline in average surface pH. pH is a logarithmic scale, so a small numerical drop is not a small chemical change. A decrease of a few tenths represents a substantial increase in hydrogen ion concentration, an intensified chemical pressure on organisms that live at narrow tolerances. A second reaction matters for life that builds shells and skeletons. Hydrogen ions combine with carbonate ions, reducing carbonate availability in seawater, and that reduction changes the saturation state that controls how easily minerals form. Calcifying organisms rely on carbonate to build calcium carbonate structures. Corals, pteropods, many plankton, and some shellfish face higher energetic costs as carbonate declines, because they must work harder to concentrate ions at the site of calcification. In simple terms, the water becomes less friendly to shells. The minerals can still form, but the margin of safety shrinks, and in some regions the water can even become corrosive to aragonite, one of the more soluble forms of calcium carbonate. This is not the same as heat stress, even when both happen together. Warming can bleach corals through thermal stress, while acidification weakens calcification even in cooler water, and the combined burden can be greater than either alone. In reef scenes, the difference is visible in slow motion. Heat can drive corals to expel symbiotic algae, turning them pale, while acidification can thin skeletal growth, quietly reducing the reef's ability to keep pace with waves and erosion. The chemistry is measurable with ship surveys, moorings, and autonomous floats. Scientists track pH, dissolved inorganic carbon, alkalinity, and the saturation state of aragonite and calcite, and they cross-check instruments with discrete water samples. Alkalinity matters because it represents the ocean's capacity to neutralize added acid. It is shaped by geology and river inputs, and it helps determine how strongly pH responds when CO2 rises, one reason different basins respond at different rates. The pattern is coherent across basins, with regional differences driven by circulation and biology. Upwelling regions can acidify faster at the surface because deep waters already carry high CO2, and when they rise they bring that chemistry with them. In coastal upwelling zones, the sea can look rich and productive, green with plankton. Yet the same upwelling that feeds ecosystems can also deliver low pH water to the surface, creating episodes that stress shellfish hatcheries and wild populations. The ocean also has buffering capacity, but it is not infinite. Buffering depends on alkalinity and mixing, and it can be overwhelmed when CO2 rises quickly, because chemical equilibrium shifts faster than the slow processes that restore balance. A crucial point is timescale. Surface waters can acidify within years, while deep ocean adjustment takes centuries as mixing slowly carries carbon downward, and that delay creates a long tail of commitment. That lag creates an invisible threshold problem. Even if emissions slowed, the ocean would continue to absorb CO2 until air and sea approach a new equilibrium, and the chemistry would keep drifting long after headlines moved on. Acidification also interacts with food webs in ways that are hard to reduce to one headline. Some species may adapt or shift ranges, while others lose competitive ground, and the winners and losers can reorganize ecosystems. Plankton changes can propagate upward because they are the base of marine ecosystems. Small chemical shifts can alter growth rates, reproduction, and predator-prey timing, and those timing mismatches can ripple into fisheries and seabird colonies. There is also a behavioral dimension that is easy to overlook. Some studies suggest altered CO2 conditions can affect sensory cues in certain fish and invertebrates, raising the question of how many ecological interactions rely on chemistry we rarely consider. We keep the central question in view by separating what is observed from what is projected. Observations show declining pH and carbonate saturation in many regions, with strong agreement across methods and a clear link to rising atmospheric CO2. Projections add scenarios, because future chemistry depends on future emissions and circulation. Models are tested against observed trends, but uncertainty grows as we look further ahead, especially where biology and circulation can amplify or dampen change. In the background of this modern story is a longer history. The ocean has experienced acidification events in deep time, and the sediment record suggests rapid carbon injections can coincide with ecological disruption, an unsettling echo, even if today's details differ. Now we move from oceans to frozen ground, where carbon has been stored out of reach. Permafrost is a slow reservoir that becomes active when warmed, and its activation is one of the clearest examples of a hidden threshold. Permafrost is soil and sediment that stays frozen for at least 2 consecutive years. In many places it has remained frozen for millennia, storing organic carbon that never fully decomposed because cold temperatures slowed microbial metabolism. In tundra landscapes, the surface can look deceptively simple: moss, low shrubs, and shallow ponds under a wide sky. Beneath that surface lies a freezer of roots, peat, and ancient plant material, packed into ice-rich ground. When permafrost thaws, microbes can access that organic matter and break it down. In oxygen-rich conditions, decomposition produces CO2, while waterlogged conditions favour methane production, because different microbial pathways dominate when oxygen is scarce. Methane matters because it is potent in the near term. Molecule for molecule, it traps more heat than CO2 over decades, even though it lasts a shorter time in the atmosphere, so it can accelerate warming during critical windows. Its atmospheric lifetime is roughly a decade, with oxidation turning it into CO2 and water. That short lifetime means methane responds quickly to changes in emissions, for better or worse, and it also means today's methane can become tomorrow's CO2. Permafrost emissions are not a single switch, and they vary by landscape. Thaw can be gradual from the surface downward, or abrupt when ice-rich ground collapses into thermokarst, reshaping the land in a season. Abrupt thaw can expose deep carbon quickly, changing drainage and creating ponds that favour methane. These local shifts can scale up when repeated across wide regions, and satellite images can capture the scar patterns of collapse, spreading like a slow contagion. The mechanics are physical as well as biological. When ground ice melts, the soil structure can fail, the surface subsides, and water collects, insulating the ground in winter and accelerating further thaw. Feedback layered on feedback. What do we measure today? We measure ground temperature profiles, active layer thickness, and changes in surface subsidence using field sites and satellites, and we compare them across seasons to see whether the freezeback is keeping pace. We also measure greenhouse gas fluxes with towers, chambers, aircraft, and inversions that infer emissions from atmospheric concentrations. Each method has limits, so convergence matters, and the strongest conclusions come when independent lines of evidence agree. Current observations show thaw is occurring in many Arctic and subarctic regions. They also show high variability, because weather, snow insulation, and soil moisture control microbial activity, and because landscapes differ over short distances. Snow is not just scenery in this story. A deeper snowpack can act like a blanket, keeping the ground warmer through winter, and that winter warmth can matter as much as summer heat for long-term thaw. What remains more uncertain is the future magnitude and timing of carbon release. Models project increasing permafrost emissions with warming, but they differ in abrupt thaw representation and microbial dynamics, and those differences can change projected totals. This uncertainty is not ignorance, and it is not a reason for dismissal. It is a bounded risk in a system with known carbon stocks and known temperature sensitivity, and the bounds tighten as observations accumulate. Permafrost is also a feedback, not a primary cause. Warming triggers thaw, thaw releases greenhouse gases, and those gases add to warming, tightening the loop, and making the system harder to stabilize once it accelerates. A thought that lingers here is about timing. How much carbon can be released before societies reach lower emissions, and how much of that release becomes unavoidable because the ground has already crossed a thermal threshold. Now we return to land ecosystems that currently slow the rise of atmospheric CO2. Forests and soils act as sinks, but sink strength is not guaranteed, and it can weaken without any single dramatic event. From above, forests look like a continuous surface, dark green, textured, and alive. Yet the sink is the sum of countless local decisions by plants: when to open stomata, when to grow, and when to conserve water. CO2 fertilization can increase plant growth by making photosynthesis more efficient. That effect is real in experiments and observations, but it is limited by nutrients, water, and heat, and it can saturate as other constraints tighten. Nitrogen and phosphorus constraints can cap long-term gains, especially in older forests. If nutrients are scarce, added CO2 cannot be fully translated into new tissue, so the theoretical boost becomes smaller in practice. Drought can close stomata and reduce uptake, even when CO2 is abundant. The plants need to conserve water can override the chemical advantage of higher CO2, and prolonged drought can also increase mortality and reduce leaf area. Heat stress can push ecosystems toward respiration and loss. When nights stay warmer, plants and microbes can release more carbon, narrowing the net sink, and in some regions the balance can flip during extreme heat waves. Soils are a major part of the story, and they respond to temperature and moisture in complex ways. Warming can speed microbial decomposition, but drying can slow it, so the net effect depends on how climate shifts the local water balance. Wildfire adds a fast pathway that converts stored biomass into atmospheric carbon. Fire also changes albedo and hydrology locally, but its global carbon impact depends on regrowth and repeated burning, and on whether forests return or transition. In some regions, forests can recover carbon over decades after a fire. In other regions, repeated heat and drought can shift vegetation types, reducing future storage and turning a once stable sink into a more volatile reservoir. Year-to-year sink strength varies with climate modes like El Niño and La Niña. During hot, dry years, tropical land sinks often weaken, and atmospheric CO2 rises faster, a signal that can be seen in global monitoring networks. This variability can confuse public perception if we focus on single years. The long-term trend is clearer when we integrate across decades and multiple datasets, and when we remember that noise does not erase a persistent signal. We measure land sinks through inventories, eddy covariance towers, satellite greenness proxies, and atmospheric inversions. Each approach sees a different slice, so agreement builds confidence, and disagreement becomes a clue about missing processes. The same discipline applies as in earlier chapters. We do not claim every forest change is climate-driven, yet we quantify how warming and drying shift probabilities and how extremes can change the direction of net carbon flow. Across ocean, permafrost, and forests, the pattern is a rebalancing of reservoirs. Slow stores become active, fast exchanges intensify, and the atmosphere records the net result, an audit trail written in parts per million. This is the chemistry side of the baseline shift. Energy imbalance warms the system, and warming changes how carbon moves and what forms it takes, so the physical and chemical narratives become inseparable. The unsettling part is that thresholds can be invisible until crossed. A small average warming can unlock microbial activity, reduce carbonate saturation, and tip ecosystems from sink to source, and the transition can look gradual until it suddenly is not. Still, we keep the story anchored to measurement. The unusual signal is not one dramatic data point, but the coherence of chemical trends across independent observing systems, each with its own instruments, errors, and verification. Carbon also links chapters that seemed separate. The ocean's heat memory now has a chemical memory, and the cryosphere's retreat now has a carbon consequence, and both memories lengthen the shadow of present choices. We end with a pivot to another hidden system that is often misunderstood. Beneath the atmosphere and oceans lies Earth's magnetic field, measurable and changing and surrounded by louder myths. Next, we separate sensational claims from observatory records. We follow the field's slow drift and ask what it does and does not mean for life at the surface. For most of human history, Earth's magnetic field felt like a permanent, silent roof, steady enough to trust, invisible enough to ignore. Now magnetic observatories and satellites show a moving pattern, one that is subtle, measurable, and surprisingly easy to misunderstand. This chapter returns to the central question with a calmer lens. What is changing right now? What is normal drift? And what do the best records say without exaggeration or panic? When the field shifts, it does so with physics, not intention. Yet our instincts still reach for omens. The magnetic field is not a single bar magnet buried in rock, waiting to fade like a battery. It is a living flow pattern created far below the crust, inside the liquid outer core where motion and electricity are inseparable. Earth's outer core is mostly iron alloy, mixed with lighter elements such as sulfur, oxygen or silicon, and hot enough to stay molten. Under pressures of millions of atmospheres, this metal flows like a dense ocean, and it conducts electricity extremely well. Heat escapes from the deep interior toward the mantle, and that slow leak matters. It is powered by leftover heat from formation, by radioactive decay in the mantle, and by the gradual freezing of the inner core which releases latent heat. That heat loss drives convection in the outer core. Buoyant fluid rising, denser fluid sinking, always seeking balance in a restless loop. As iron-rich fluid moves, it carries electrical charge with it, and that moving charge is the seed of magnetism. Earth's rotation organises that churning in a way that feels almost architectural. The Coriolis effect stretches convection into columns aligned with the rotation axis, turning small turbulence into large-scale structure that can persist. In plain terms, rotation makes the core's flow prefer spirals and columns rather than random sloshing. Those organised motions are essential, because a disordered flow tends to cancel itself out, while coherent flow can build a durable global field. Moving conducting fluid in an existing magnetic field induces electric currents, and those currents create new magnetic fields in return. This feedback loop can sustain itself as a geodynamo, provided energy keeps driving motion and the flow stays organised. The result is a field that is mostly dipolar at the surface, with a north and south magnetic pole that resemble a tilted bar magnet. Yet, it is never perfectly dipolar, and it never truly stands still, because the engine never stops adjusting. If we could see the field lines, the planet would look threaded with luminous arcs. They would rise near one hemisphere, sweep through space and fold back down, an invisible architecture that is smooth in some places and kinked in others. The field is also a shield, but it is not a sealed dome. It deflects many charged particles from the solar wind, and it shapes the Van Allen radiation belts that surround Earth like nested rings of trapped energy. That shielding is why the field matters to technology and exposure, especially above the atmosphere where satellites live. It is also why changes in the field attract fear, and sometimes attract myths, because shield sounds like a promise. We start with what is observed now, because measurement is the only antidote to speculation. The field changes on human timescales through secular variation, slow drift in strength and direction that reflects evolving flow at the top of the core. Compass north is not geographic north, and it never has been. Even in the age of wooden ships and hand-drawn charts, magnetic north wanders because the core flow that generates the field keeps evolving, and because the field is slightly tilted and slightly lopsided. For navigators, that difference has always required correction, and the correction has always changed with time. Early mariners learned declination by experience, then by maps, and eventually by global models that must be revised as the field shifts. Over the last centuries, the dipole moment has declined, and that decline is one of the simplest global summaries we can compute. The global average strength has weakened by roughly 10% since the 19th century, though the change is uneven and regionally complex. Uneven is the key word because the surface field is not a single knob turning down. Some regions weaken while others strengthen, because the field at the surface is a patchwork of contributions from different core structures and different wavelengths of magnetic pattern. Even the global average hides a geography of highs and lows, like weather maps hide local storms. The dipole is the largest component, but smaller scale features can dominate what a satellite experiences along a particular orbit. One region has become the headline, partly because it sits under busy satellite corridors. Over the South Atlantic, the field is unusually weak, and the weak patch has been expanding and drifting in a way that is clear in modern maps. This is the South Atlantic anomaly, a broad zone stretching from South America toward southern Africa. It is not a hole in the field, but it is a real minimum, a dent in the shield where the radiation belts dip closer to Earth. Visually, on a field strength map, it looks like a bruise spreading across the ocean. Contours crowd together, colours deepen, and the minimum slides westward over time, as if the planet was slowly turning a hidden dial beneath the Atlantic. The anomaly matters because a weaker field lets more energetic particles reach low Earth orbit, where many satellites operate. Spacecraft passing through can experience higher radiation doses, more frequent electronics upsets, and a greater need for protective operational routines. Some instruments see it directly as noise, sudden spikes, or corrupted data frames. Others suffer quietly, accumulating damage in semiconductors and solar panels, where energetic particles knock atoms out of place and slowly degrade performance. The anomaly is also a clue about the deep engine, not just a hazard zone for hardware. It reflects how the core field is shaped by flows and by the boundary conditions imposed by the lower mantle, which can steer convection and concentrate magnetic flux. The mantle is solid rock, yet it is not uniform, and its thermal structure matters. Hotter or cooler patches at the core. Mantle boundary can alter how heat escapes, nudging the pattern of core flow that ultimately shapes the field we measure. To see that pattern clearly, we rely on modern mapping. Because the field is not static and the ocean is vast. Ground observatories provide long time series with excellent stability, but they are sparse over oceans and remote regions where the anomaly is prominent. Satellites fill that gap by measuring the field globally, over and over in repeated sweeps. They do not measure the core directly, but they measure the magnetic signature that reaches space, and they do it with consistent geometry. The European Space Agency's Swarm mission is central here, because it was designed to separate overlapping signals. 3 satellites fly in coordinated orbits, allowing scientists to compare measurements at different altitudes and along slightly different tracks. Swarm measures vector and scalar magnetic fields with high precision, and it does so continuously as it circles Earth. That precision matters because the changes we care about are small compared to the total field, and because other magnetic sources can masquerade as core change. It helps disentangle the core field from crustal magnetism and from currents in the ionosphere and magnetosphere, which vary with sunlight and space weather. In other words, Swarm turns a noisy symphony into identifiable instruments, so the deep baseline can be traced. That separation matters, because the field we feel is a sum of sources, stacked in space and time. The core dominates at long wavelengths, the crust adds smaller fixed features, and space currents add rapid variability that can change within minutes. When swarm data are combined with observatory records, the secular variation becomes a moving map rather than a static globe. The South Atlantic anomaly appears as a drifting low, not as a sudden rupture, and its edges are gradual rather than sharp. The dipole axis also continues to shift, and that shift is not merely academic. Magnetic north has accelerated its motion in recent decades, sliding across the Arctic towards Siberia, and navigation models must be updated more often to keep pace. That acceleration is a reminder that the core's flow is not constant, even if it is slow by human standards. A change in flow pattern at the top of the core can redirect magnetic flux, and the surface responds like a compass needle following a moving target. This is where the story can be distorted, because a weakening dipole sounds like a countdown. A weakening dipole does not automatically mean an imminent reversal, and it does not mean the shield is collapsing tomorrow, even if headlines prefer urgency. To understand what it could mean, we need deep time, because the field has a long memory. The magnetic field has reversed many times, and the rock record preserves that history with a fidelity that is both elegant and humbling. Reversals are not guesses, and they are not inferred from a single strange measurement. When lava cools, iron-bearing minerals lock in the direction of the ambient field, creating a magnetic snapshot that can persist for hundreds of thousands or millions of years. As molten rock cools through a critical temperature, magnetic domains in minerals such as magnetite align with the field and then freeze in place. That process, thermoremanent magnetization, turns a volcanic flow into a page in Earth's magnetic diary. Sediments also record the field more gradually, and their strength is continuity. Magnetic grains align as they settle through water, and over time they build a continuous tape of direction and intensity, later compacted into layered archives. Those layers can be dated with other tools, including radiometric methods and correlations to climate markers, which helps anchor magnetic changes in time. It is not perfect, but it is strong enough to reveal patterns that repeat across continents and oceans. By sampling sequences of flows and sediment cores, scientists reconstruct polarity changes across many intervals. The pattern is irregular, with long, stable intervals and clusters of shorter events, suggesting the dynamo has preferred states but no strict schedule. A full reversal typically unfolds over thousands of years, not days or decades. The field weakens, becomes more complex, and then re-establishes with opposite polarity, as if the dynamo reorganizes its dominant mode rather than simply flipping a switch. During that transition, the dipole component can shrink while smaller components grow, producing a multipolar field. To a mapmaker, it would look like the familiar two-pole pattern breaking into several lobes that migrate and compete across the globe. There are also excursions, which are failed reversals or large departures from the usual dipole, and their existence complicates simple narratives. They can last centuries to a few thousand years, then the field returns to its prior polarity after a period of instability. The Lachamps excursion, around 41,000 years ago, is one example that has been studied in detail. It is recorded in lavas and sediments, and it coincides with a strong dipole weakening that left a clear global signature. In some records, the field intensity during Lashom appears to drop dramatically, which would have allowed more cosmic radiation into the atmosphere. That increased radiation likely boosted the production of isotopes, such as carbon-14 and beryllium-10, leaving chemical fingerprints that echo the magnetic one. These events show that low field strength can happen without permanent reversal, and that the system can rebound. They also show that the field can recover, even after dramatic complexity, which is an important constraint on worst-case storytelling. The timescales matter for risk, because human systems operate on years and decades, not millennia. A reversal is not a switch flipped in a day, and it is not a cinematic disaster that wipes the surface clean in a single dramatic moment. During a reversal, the field does not vanish everywhere at once, and it does not drop to zero globally. It becomes multipolar, with several lobes and local regions of stronger and weaker shielding, meaning the experience would vary by latitude and longitude. That spatial variation is easy to overlook, yet it is central to realism. Even today, the field's strength differs by a factor of roughly 2 across Earth's surface, and life and technology already operate within that uneven landscape. Life has persisted through many reversals, and that persistence is not a trivial footnote. It does not prove there are no effects, but it does constrain the most extreme claims, because ecosystems have repeatedly crossed these intervals without evidence of routine global collapse. So what effects are plausible, and what would we actually notice if the field weakened further? A weaker field can allow more cosmic radiation into the upper atmosphere, and it can increase auroral activity at lower latitudes, bringing polar lights to skies that rarely see them. Auroras are not just pretty curtains of light, but visible evidence of particles guided by magnetic lines into the atmosphere. In a weaker or more complex field, those pathways can shift, widening the zones where energetic particles collide with oxygen and nitrogen and make them glow. The largest practical consequences today are technological, because we have placed delicate electronics in space and stretched conductive networks across continents. Satellites are more vulnerable to energetic particles, especially in low-field regions like the South Atlantic anomaly, where shielding is already reduced. Radiation can cause single-event upsets in electronics, flipping bits in memory, or triggering false commands. It can also cause cumulative damage, gradually degrading solar panels, increasing noise in sensors, and shortening component lifetimes in ways that are expensive and sometimes mission-ending. Operators already respond with procedures that are pragmatic rather than dramatic. Some satellites power down sensitive instruments while crossing the anomaly, others schedule critical operations outside it, and mission planners account for cumulative dose when designing orbits and shielding. In imagery, this looks like quiet choreography, timelines, checklists, and automated mode switches timed to invisible geography. The anomaly becomes a region on a mission map crossed in minutes, yet planned for years in advance. High-altitude aviation is another exposure pathway, particularly on polar routes where magnetic shielding is naturally weaker and where storms funnel particles downward. During strong solar events, radiation levels at flight altitudes can rise, and airlines sometimes reroute to lower latitudes or lower altitudes. The magnetic field is part of that risk calculus, but it is not the only factor, and it is not always the dominant one. Solar activity and geomagnetic storms can dominate short-term exposure changes, producing spikes that matter more than slow secular drift. Navigation is also affected in ways both mundane and consequential, because the field is a reference frame. Magnetic declination changes over time, and compasses must be corrected with updated models, whether they are printed on charts or embedded in software. Modern navigation relies heavily on GPS, inertial systems, and network timing, but magnetics still matter as a resilient backup. Aircraft backup systems, marine navigation, and some drilling operations depend on accurate field models, especially where a few degrees of error can mean kilometers of drift. Even smartphones contain magnetometers, and they inherit the same problem in miniature. When the field changes, calibration and modelling become more important, because the sensor is stable, but the planet beneath it is not. Infrastructure can be affected indirectly through geomagnetically induced currents, which are driven by space weather rather than by slow core drift. During strong solar storms, changing magnetic fields induce electric fields at Earth's surface, driving currents in long conductors like power lines and pipelines. Those currents can stress transformers and disrupt grids, as past storms have demonstrated in real-world outages and near misses. The field's geometry influences where induced currents concentrate, but storm strength remains the main trigger, and preparedness is the practical lever. This chapter stays disciplined about what the field does not do, because confusion thrives where boundaries are vague. Earth's magnetic field does not control the greenhouse effect, and it does not drive modern global warming, despite the appeal of a single hidden cause. The warming story is an energy balance story confirmed by spectroscopy, satellite observations, and ocean heat uptake. Magnetic changes do not provide the radiative forcing needed to explain observed trends, and the timing does not match the dominant drivers we can measure. Magnetism also does not cause earthquakes or volcanic eruptions in any established physical mechanism. The core and mantle interact through heat flow and long-term dynamics, but not in a way that links field drift to daily tectonics or to sudden ruptures in the crust. So why does the field's change still feel ominous, even when the science is careful? Because it is a deep Earth signal we can measure in real time, and it reminds us the planet has internal dynamics that do not consult our calendars. There is also a psychological edge to it, because the field is both protective and unseen. When something invisible is described as a shield, any change can sound like vulnerability, even if the actual change is gradual and manageable. The mystery is real, but it is bounded by evidence and by physical constraints. The field is restless, and the restlessness is expected in a convecting, rotating, conducting core that is constantly balancing heat loss, rotation, and magnetic feedback. The unusual part is not that the field changes, because it always has, and it always will. The unusual part is how clearly we can now watch it change, and how quickly misinformation can outrun the data that were designed to steady us. We return to the instruments because they keep the story honest and anchored to reality. Swarm, observatories, and paleomagnetic records form a chain across scales, from years to millions of years, and each link checks the others. That chain lets us separate secular variation from reversal dynamics, which operate on very different timescales. It also lets us distinguish local anomalies from global collapse narratives, because a regional minimum is not the same thing as a planetary failure. Still, the South Atlantic anomaly remains a watchpoint, and not because it is a prophecy. Its growth and drift test are models of core flow, and they matter for the satellites we depend on for communication, weather forecasting, and Earth observation. Models assimilate observations and infer flow at the top of the core, using the way the field changes as a constraint. They suggest evolving patches of reversed flux under the South Atlantic contribute to the surface minimum, like submerged eddies shaping the surface of a sea. Those inferences are not direct images, and uncertainty remains, because we cannot place instruments inside the core. Yet the broad conclusion is consistent. Core dynamics can create regional weakening without implying imminent reversal, and the present trend fits within known dynamo behavior. The field story also connects to earlier chapters in an unexpected way, through the idea of stored memory. Like ocean heat and ocean chemistry, magnetism carries memory, and it changes with lag dynamics that can take years to observe clearly. The ocean stores heat and carbon for decades to centuries, releasing and absorbing them with delays that complicate simple cause and effect. The core stores momentum and magnetic structure on its own timescales, and it reveals change as slow drift rather than sudden confession. Across systems, the method stays the same, even when the subject feels mysterious. We compare independent measurements, we quantify uncertainty, and we resist the temptation to turn every trend into prophecy, because the planet is complex but not unknowable. Now we pivot toward the solid Earth we can feel. If the magnetic field is one deep signal, the next question is about the crust and mantle, earthquakes, volcanism, and claims of increased activity that circulate whenever the ground reminds us it can move. We will ask the same disciplined question again, and we will keep the same standard of evidence. What is actually changing? What is normal variability? And what do global catalogues and geophysical networks truly show when the noise is filtered from the signal? The ground is not a fixed stage. It is a moving boundary between deep heat and surface life. Beneath our feet, rock behaves like a spring and a slow-flowing fluid at the same time, depending on depth, temperature, and time. After the magnetic field, we pivot to the solid Earth we can feel. The question is familiar and urgent. Are earthquakes and eruptions increasing right now, or are we simply noticing more? It sounds like a simple trend line, yet the answer hides inside how we measure, how we remember, and what we choose to count. We start with what is observed now, because measurement is the only antidote to speculation. Seismometers, satellites, and global catalogues have turned rumble into numbers. In the control rooms, faint wiggles become timestamps, coordinates, and magnitudes, clean digits that feel authoritative. Yet numbers can mislead when the record itself changes, and when the quiet parts of history were never recorded. An earthquake is a sudden release of stored elastic strain. Plates move steadily, faults lock, stress accumulates, then friction fails. In the locked zone, the crust deforms by millimeters each year, like a bent ruler that refuses to snap. When it finally slips, the rupture races along the fault at kilometers per second, and the planet rings. The rupture radiates seismic waves that instruments convert into magnitude and location. P waves arrive first, compressing and expanding rock like a sharp knock. SE waves follow, shearing the ground side to side, and surface waves roll in last, often the waves that topple buildings and twist bridges. Modern networks compare arrival times across stations, and triangulation turns a global vibration into a point on a map. Magnitude is not a single scale, and that matters for trends. Older catalogues often used local magnitude, the original Richter approach, which worked well for nearby moderate events in Southern California. But local magnitude saturates for large earthquakes, meaning the scale stops growing even when the rupture does. Modern global work relies on moment magnitude tied to physical rupture size, so the biggest events do not get artificially flattened. Moment magnitude is based on seismic moment. Moment combines fault area, average slip, and rock rigidity. In plain terms, it asks how big the tear was, how far it moved, and how stiff the rock was while it broke. That physical anchor is why moment magnitude scales with energy release in a way that stays consistent for the largest events. Magnitude is logarithmic, which makes intuition unreliable. Each whole number step is about 10 times larger wave amplitude. Energy rises faster still, so a magnitude 7 dwarfs a magnitude 5. The difference is not 2 units of drama, but hundreds of times more energy, enough to change coastlines, or to shift the rotation of the Earth by tiny measurable amounts. This is why small quake counts can surge while hazard stays similar. A catalogue can double its tiny events without adding a single damaging rupture. The public hears more earthquakes and imagines bigger earthquakes, even though the added events may be too small to feel. The ground can be chattering more in our data while staying equally dangerous in reality. Global seismicity follows a statistical rule called the frequency magnitude relationship. Many small quakes occur for every moderate quake. Far fewer large quakes occur, and the drop-off is steep. On a log plot, the pattern becomes a near straight line, an eerie simplicity emerging from chaotic fracture. The Gutenberg-Richter relation is the backbone of this pattern. It says that as magnitude increases, event counts fall roughly exponentially. It is not perfect everywhere, because fault networks differ and stress regimes vary. Yet it is robust enough to test claims, and it gives us a disciplined way to separate a real shift from a louder microphone. If the Earth were truly becoming more seismically active, we would expect changes at the top end. Large events are detected globally even with sparse instruments. Their record is less sensitive to network upgrades, because great earthquakes push waves through the entire mantle and around the globe. Even a century ago, they left unmistakable signatures on paper drums. So we look first at the big quakes. For roughly the last century, the rate of magnitude 7 and above is variable, but not rising clearly. Clusters happen, then quiet years follow, and the long-term average holds. The planet does not behave like a metronome, and our brains dislike that kind of irregularity. The early 20th century record is not as complete for small events. It is still adequate for the largest earthquakes, because they shake the whole planet. They were recorded on distant stations even in the analog era, when ink traced waves onto rotating cylinders. Those early seismologists built global cooperation from telegrams and mailed paper. Slow science, but surprisingly durable. The modern era adds dense networks and digital telemetry. That changes what we can see, not necessarily what is happening. Detection thresholds drop, and the catalogue fills in with events once missed. In some regions, what used to be silence becomes a constant shimmer of microquakes, like static resolving into speech. This is detection bias, and it is central to the chapter. When instruments improve, the apparent baseline shifts. The Earth did not suddenly start producing magnitude 2 quakes in the 1970s. We simply began hearing them because sensors got quieter, timing got sharper, and computers got fast enough to scan continuous data. Network growth is uneven across the globe. Wealthy regions and coastlines gained stations earlier, remote oceans, polar areas, and parts of the global south filled in later, changing completeness over time. On a world map, station dots spread like constellations, dense over North America, Europe, and Japan, thinner across wide interiors and open seas. Completeness is the magnitude above which we trust the catalogue to be nearly complete. Above that threshold, trends are meaningful. Below it, changes can reflect listening better rather than shaking more. Completeness is not a philosophical idea, but a practical limit, what the network could reliably detect at a given time. We can test completeness by looking for the magnitude where counts stabilize against network changes. We can also compare independent catalogues and see where they agree. Agreement at high magnitudes is strong because big earthquakes are unmistakable. Disagreement grows at low magnitudes, where a few missing stations can mean thousands of missing events. Short-term clustering is another trap. Earthquakes trigger earthquakes through aftershocks. A single great rupture can produce months of elevated activity that looks like a new normal. The main shock rearranges stress like a snapped branch whipping through a thicket. Some nearby faults are pushed closer to failure, while others are temporarily relaxed. Aftershocks follow their own statistics. Their rate decays with time, often roughly as a power law. The first day can be frantic, then the sequence thins, then it fades into background noise. If you start counting during a busy year, you can convince yourself the planet is escalating, even though you are watching a natural echo. There is also the problem of memory in human attention. A few headline events can dominate perception for years. The catalogue does not care about headlines, but people do. We remember where we were when the shaking started, and we forget the quiet decades that made it feel unusual. We separate tectonic earthquakes from induced ones because the causes differ. Induced seismicity can rise sharply in specific regions. It can be driven by fluid injection, extraction, or reservoir loading. These events are often smaller than major tectonic quakes, yet they can be frequent enough to change a region's sense of safety. Injection changes pore pressure in faults. Higher pore pressure reduces effective normal stress, making slip easier. In plain terms, fluids act like a lubricant in a wedge, lowering the frictional grip that holds a fault shut. The stress field does not need to change much for the failure threshold to be crossed, because the threshold itself is being altered. This is not a global trend, but it is a real local risk. It shows how human activity can modulate seismicity without changing plate motion. It also shows why careful attribution matters, because a rise in one place can be mistaken for a rise everywhere. The Earth's statistics can be distorted by a handful of industrial basins. Now we widen the lens to volcanoes. Volcanoes are the surface expression of melting, buoyancy, and pathways through rock. They're tied to plate boundaries, hotspots, and rifts. Yet each system has its own tempo. Some are open conduits that breathe often, while others are sealed pressure cookers that wait. Eruptions are harder to count than earthquakes. Many eruptions are small, remote, or submarine. Historical records depend on ships, settlements, and written archives, which are uneven in time and geography. A distant island volcano might erupt for weeks, and the only witness could be a passing cloud deck. Modern databases compile these records into global catalogues. The Smithsonian's Global Volcanism Program is a key reference. It tracks eruption dates, styles, and volcano histories with continual revision. That revision matters because new fieldwork can reveal old ash layers, and old myths can become confirmed eruptions. As with earthquakes, completeness is the first question. The record of large explosive eruptions is better than the record of small effusive events. Older centuries undercount minor eruptions, especially in remote arcs. Even the definition of an eruption can shift, because a brief ash puff and a months-long lava flow leave very different traces. That undercount can create a false upward trend. As observation improves, the catalogue appears to accelerate. The Earth may be constant while our reporting becomes comprehensive. In the visuals, the timeline looks like it wakes up, yet the awakening may belong to us, not to the mantle. Satellites changed volcanology the way digital seismology changed earthquakes. Thermal sensors detect hot lava and domes. Ash clouds are tracked in infrared and visible bands even over oceans. From orbit, a volcano's heat signature can glow through night and weather, and a plume can be followed like ink in water. Gas measurements also expanded the record. Sulfur dioxide plumes can be mapped from space. That reveals eruptions that would once have been missed or misdated, and it helps distinguish volcanic clouds from ordinary weather systems. The chemistry of a plume becomes a fingerprint, an atmospheric clue pointing back to a vent. When we correct for completeness, the long-term statistics look steadier. The number of volcanoes erupting each year varies. The variation often fits natural clustering rather than monotonic increase. Some years are busy across multiple arcs, and other years feel quiet, even though magma is still moving below. Clustering in volcanism has multiple causes. Regional tectonic episodes can open pathways. Magma systems can respond to stress changes, and eruptions can alter local plumbing. A large eruption can decompress a chamber, change fracture networks, and influence what happens next, sometimes suppressing activity, sometimes priming it. Large eruptions are rare, and their timing is irregular. A few decades without a major event does not mean the system is calming. A few events close together do not prove acceleration. The deeper question is whether the probability distribution is shifting, or whether we are watching normal randomness play out. We bring the central question back into focus. What measurable changes are happening now, and what is perception? The answer is mixed. Globally, the strongest evidence does not show rising rates of the largest earthquakes or eruptions, but the planet's surface is being reshaped quickly, and that reshaping can matter at the margins. Yet the story does not end with nothing is happening. The planet's surface loads are changing fast. Ice is melting, sea level is rising, and water is being moved and stored in new places. Mass is being redistributed across continents and oceans, and the crust is sensitive to weight, especially when faults are already close to slipping. This is where climate enters the solid Earth story without sensationalism. The crust responds to changing loads. Remove weight and the lithosphere rebounds, altering stress on faults and magma systems. Add weight and the crust flexes downward, pushing fluids and changing the pressure conditions that control failure. We have seen this before in deep time and recent history. After the last ice age, thick ice sheets retreated. Regions like Scandinavia and Canada have been rising ever since. Ancient shorelines now sit high above modern seas, like ghost coasts that mark where water once stood. This post-glacial rebound is measurable today. GPS stations record uplift of millimeters to centimeters per year. The mantle flows slowly, and the surface responds with lagged motion. In the visuals, time-lapse arrows climb upward, and the land seems to inhale after a long compression. Rebound changes the stress field. It can unclamp some faults and load others. It can alter the timing of earthquakes in regions already near failure. The stress changes are modest compared with plate driving forces, yet they can be decisive when the system is balanced on a threshold. Evidence links deglaciation to changes in seismicity in some areas. The strongest signals appear where ice was thick and retreat was rapid. The effect is regional, not global. It is a reminder that the solid Earth is not isolated from the surface, even when the coupling is subtle. Volcanoes can also respond to unloading. Reducing pressure can increase melt production in the mantle. It can also ease the ascent of magma by changing the stress state of the crust. A small pressure drop can allow dissolved gases to exsolve, expanding magma and increasing buoyancy, like opening a carbonated bottle deep underground. Iceland is often discussed because it sits on a ridge and a hotspot. It also experienced major deglaciation. Studies suggest eruption rates increased after ice retreat in the past. In aerial shots, black lava fields spread beneath bright ice caps, and the contrast makes the coupling visible, fire and ice sharing a boundary. The key word is plausible, not proven everywhere. The physics is sound, but the Earth is noisy. Magma supply, tectonics, and local structure can dominate the signal. A volcano is not a simple gauge, because each plumbing system has its own geometry, its own history, and its own bottlenecks. Greenland and Antarctica raise a modern question. As ice mass declines, will rebound and stress changes alter seismicity near their margins? Models suggest stress perturbations are possible in some fault systems. The margins are complex with hidden faults, changing ocean loads, and evolving ice dynamics that can shift forces year by year. These changes are small compared to tectonic stresses, yet they can matter near thresholds. Faults fail when they are close to failure. A modest stress change can shift timing without creating new tectonics. The unsettling idea is not that climate creates earthquakes, but that it can nudge the schedule in places already primed. Water loads also matter, and we already have direct examples. Reservoir-induced seismicity is well documented. Filling a large reservoir adds weight and changes pore pressure in surrounding rock. The water seeps into fractures, and the added pressure can propagate along faults, sometimes kilometers from the shoreline. Some reservoirs correlate with increased local earthquakes. The mechanism is not mysterious. It is stress plus fluids, acting on faults that were already there. In footage, a calm lake surface hides the slow infiltration below, and the contrast between serenity and strain becomes part of the story. Seasonal hydrology can modulate seismicity too. Heavy rains and snowmelt change groundwater and surface loads. In some regions, small but measurable seasonal patterns appear in microseismicity. The signal is faint, but it is a clue that the crust responds to cycles we experience as weather. Sea level rise adds load to continental margins. It also redistributes mass, changing stress in subtle ways. The expected effects are small, but they are part of a coupled planet. Over long coastlines, even centimeters of sea level represent vast weight, spread like a thin blanket across the shelf. This is the same logic as earlier chapters about memory and lag. The ocean stores heat and expands for decades. The cryosphere loses mass with long commitments. The solid Earth responds with its own delayed adjustments. Some responses are immediate and others unfold over centuries because the mantle's viscosity sets the pace. We underline the discipline again. A mechanism is not a trend. A stress perturbation is not proof of a global increase. The question is what the records show and what uncertainties remain. Science advances by separating what could happen from what is already happening and by quantifying the difference. We return to catalogues with this nuance in mind. Global earthquake energy release is dominated by rare great events. Over the instrumental era, it fluctuates with clusters, but it does not climb steadily. One megaquake can dominate a decade of energy totals, making the graph jump like a heartbeat. For volcanoes, the best global compilations show variability and clustering. They do not show a simple modern surge once reporting bias is addressed. The long record is incomplete, so confidence is bounded. The deeper past is written in ash layers and lava sequences, and those archives are unevenly preserved. Bounded does not mean trivial. It means we state what we know and what we cannot. It means we do not convert uncertainty into fear or into denial. In a world of instant charts, restraint becomes a kind of courage, because the ground does not reward exaggeration. Now we shift from trends to hazards. Even if the rate is stable, risk can rise. Risk is hazard times exposure times vulnerability, and exposure has changed dramatically. The same physical Earth now intersects with a denser, more interconnected civilization. More people live in cities on faults and near volcanoes. Coastal megacities sit on soft sediments that amplify shaking. Infrastructure networks are denser, more interdependent and more fragile to cascading failures. A rupture that once damaged a few roads can now disrupt ports, data links and power grids across a region. A stable earthquake rate can still produce rising losses. More buildings, more pipelines, more power lines, and more data centers sit in harm's way. The same magnitude event now strikes a different world. Even when engineering improves, the sheer concentration of assets changes the stakes. Volcanic risk also scales with exposure. Air travel crosses ash corridors daily. A moderate eruption can disrupt global logistics, not by killing people, but by grounding fleets and rerouting supply chains. Fine ash can sandblast jet engines and contaminate airframes, so caution becomes mandatory, regardless of how often eruptions happen. Secondary hazards amplify the impact. Earthquakes trigger landslides and tsunamis. Volcanoes generate lahars, ashfall, and gas hazards that can travel far beyond the vent. The danger footprint can be larger than the eruption column, because gravity and water carry the consequences downhill. Climate change can interact with these hazards through exposure pathways. Sea level rise increases tsunami reach and coastal flooding. Heavy rainfall can increase landslide susceptibility after shaking. In saturated hillsides, the same ground motion can produce far more failure because the soil has already lost its strength. Warming can also change the cryosphere around volcanoes. Glacier-covered peaks can produce larger meltwater floods during eruptions. The hazard footprint can expand even if eruption frequency does not. In stark imagery, dark ash settles on bright ice, absorbing sunlight and accelerating melt, an interaction that is visual, immediate, and consequential. We connect this back to the conclusion theme of the series. Earth has always changed, and the ground has always moved. The unusual signal is not that earthquakes exist, but how many systems are shifting together. When oceans warm, ice retreats, and cities grow, the same old hazards meet new conditions. The baseline shift is partly physical and partly informational. We are measuring more, faster, and with finer detail. That can create anxiety that feels like acceleration. A world of constant notifications can make natural variability feel like a rising drumbeat, even when the long record stays flat. So we offer a rule for the viewer. When you hear activity is increasing, ask what magnitude range and what catalogue completeness. Ask whether the claim controls for network growth and reporting bias. Ask whether aftershocks were separated from main shocks, and whether the comparison window is long enough to mean anything. Then ask the second question, which is often more important. Even if the rate is unchanged, what has changed in exposure and preparedness? What has changed in building codes, early warning, and response capacity? A stable hazard can become a larger disaster, or a smaller one, depending on choices made long before the shaking starts. Early warning is a modern example of measurement becoming protection. Seismic waves travel slower than signals. Networks can detect a rupture and send alerts seconds before strong shaking arrives. Those seconds are short, yet they are real time, enough to switch systems into safe modes and to give people a moment to act. Those seconds can stop trains, open firehouse doors, and protect surgeries. They do not prevent earthquakes, but they convert knowledge into resilience. The same instrument revolution that confuses trends can also save lives. In the visuals, alerts ripple outward faster than the shaking itself, like a race between information and physics. Volcano monitoring follows the same pattern. Seismic swarms, ground deformation, and gas changes can signal unrest. Forecasts are probabilistic and false alarms happen, yet monitoring reduces surprise. Tilt meters can detect subtle inflation, and satellite radar can map ground movement across an entire caldera. Motion too small to see, yet too important to ignore. We keep the tone mysterious, not because the ground is unknowable, but because it is deep. The crust hides its stress until it releases it. The mantle hides its melt until it finds a path, and when the release comes, it arrives with a speed that feels sudden, even though the loading took years. The deeper mystery is how a warming surface can reach into these systems. The links are real in some places, subtle in others, and still being quantified. The planet is coupled, and coupling creates surprises. The question is not whether everything is connected, but which connections are strong enough to matter now. We close this chapter with a careful conclusion. The best global records do not show a clear modern increase in the largest earthquakes or eruptions. What is increasing is our detection of small events and our exposure to inevitable hazards. The moving ground is not new, but our world on top of it is. Now we lift our eyes from the moving ground to the space above it. Earth's changes are not isolated. Space weather and solar variability interact with our atmosphere and technology, adding another layer to the mystery from above. Now we lift our eyes from the moving ground to the space above it. Earth is not isolated. It sits inside a variable solar environment that changes by minute, by year, and by decade. For most of human history, the sun was treated as constant, a reliable lamp that rose and set, indifferent to human concerns. Modern instruments show a star with moods. The baseline of space around Earth is not empty, and it is not quiet. We start with what is observed now, because measurement is the only antidote to speculation. Space weather is not astrology. It is plasma physics measured by satellites, magnetometers, and radio signals crossing the sky. In orbit, detectors count particles and map fields. On the ground, magnetometer needles drift and snap. Across the spectrum, telescopes watch the sun in visible light, ultraviolet and X-rays, each band revealing a different layer of the star. The sun's surface is threaded with magnetic fields. Those fields are generated by a dynamo in the convection zone, where hot plasma rises, cools, and sinks again. As the sun rotates, the field lines tangle, shear, and reconnect. That magnetic activity drives sunspots, flares, and the eruptions that can reach Earth. It also shapes the corona, the sun's outer atmosphere, which glows in extreme ultraviolet like a crown of hot iron. Even when the sun looks calm to our eyes, the corona is structured and restless. The most familiar rhythm is the solar cycle. Roughly every 11 years, sunspot counts rise and fall, while the sun's global magnetic polarity flips and reorganizes. The cycle is not perfectly regular, and its amplitude varies from one peak to the next. Historically, the cycle was first quantified in the 19th century through careful sunspot records. Those early observers could not see the magnetic fields directly, yet they noticed the pattern, an astrophysical heartbeat written in ink and patience. Today, magnetographs reveal the hidden architecture that those records only hinted at. Sunspots look dark because they are cooler than the surrounding photosphere. Strong magnetic fields suppress convection, so less heat is carried upward. Yet the same active regions contain bright faculum that shine especially near the limb. When activity is high, the sun's total output rises slightly, not falls. The bright faculae more than compensate for the darker spots. The result is subtle, but it is real, an increase in total energy reaching Earth. Total solar irradiance changes by about 0.1% across the cycle. That number sounds small, and it is small compared with greenhouse forcing. Still, it is measurable, and it matters for the upper atmosphere. The bigger solar change is not in total brightness. It is in ultraviolet and extreme ultraviolet radiation, which originate higher in the solar atmosphere where magnetic activity dominates. UV can vary by several percent to far more in specific bands. Those bands control photochemistry. They determine how oxygen splits and recombines, how ozone forms and breaks apart, and how the upper atmosphere gains heat. In plain terms, UV is the sun's lever arm on the air we cannot breathe. UV is absorbed high above the weather we live in. It ionizes oxygen and nitrogen, knocking electrons loose and creating a plasma mixed into the thin air. It creates and destroys ozone. It heats the thermosphere, where air is thin but electrically alive. In the visuals, this layer is almost invisible until you show it as a glowing shell around Earth, shimmering with day-night contrast. On the day side, sunlight builds the ionosphere like a tide rising. On the night side, recombination drains it away. The sun also blows a constant outflow of charged particles. This is the solar wind, a stream of protons and electrons expanding outward from the corona. It carries embedded magnetic fields outward, and it shapes the space around every planet. The solar wind is not uniform. It has slow streams and fast streams, shocks and rarefactions, and turbulent waves that ripple through it. Near Earth, it is sampled directly by spacecraft stationed upstream, sentinels that measure speed, density, and magnetic direction. Earth's magnetic field meets that wind and forms a magnetosphere. It is a cavity carved in plasma, held open by the pressure of the geomagnetic field. It is compressed on the day side and stretched into a long tail on the night side. In animation, the boundary looks like a translucent bubble being pushed by an invisible gale. The bow shock forms ahead of it, like water piling up in front of a ship. Behind Earth, the magnetotail extends far beyond the Moon's orbit. This is where Chapter 7 returns with new meaning. The magnetic field is not only a deep Earth signal, it is also the boundary condition that decides how solar energy couples into near-Earth space. When the solar wind is steady, the system is noisy but manageable, with constant small adjustments in currents and fields. When the wind changes abruptly, the magnetosphere responds like a struck bell, ringing with waves that travel along field lines. Energy is stored, redirected, and released through currents and waves. Some of that energy becomes heat, some becomes particle acceleration, some becomes electromagnetic disturbance that spreads through the coupled system. The ionosphere is the electrically charged layer of the upper atmosphere. It forms when sunlight knocks electrons free, creating regions with different densities and conductivities. It changes with day and night, with seasons, with solar cycles, and with storms. Even its structure is layered. The D region absorbs radio waves and grows in daylight. The E region hosts currents and sporadic layers. The F region, higher and thinner, carries much of the long-range radio reflection and GPS delay. Radio communication and navigation depend on it. GPS signals pass through it and can be delayed or distorted, especially when the electron content changes rapidly. Over-the-horizon radar reflects from it. Shortwave radio can skip across oceans because of it. During disturbances, the ionosphere can develop irregularities, patches and bubbles that scatter signals. To a receiver, the effect is a flicker and a wobble, as if the sky itself were a shifting lens. The technology is precise, and the medium is alive. The thermosphere sits above the stratosphere and mesosphere. It expands when heated by solar UV and geomagnetic energy. raising density at satellite altitudes. It contracts when cooling dominates, changing the drag where satellites fly. This is the first key tension of the chapter. The Sun drives real variability in Earth's upper atmosphere, yet that variability does not automatically explain the warming measured at the surface. We separate the layers because physics demands it. Solar UV is mostly absorbed high up, where it can heat and ionize without strongly warming the ground. Greenhouse gases trap infrared lower down. The same planet can cool above while warming below. The second key tension is technological. Our civilization has moved critical systems into the very region the Sun disturbs. The modern world depends on satellites, timing signals, and long power lines that behave like antennas. We define space weather in practical terms. It is the changing conditions in the solar wind, magnetosphere, ionosphere, and thermosphere. It is driven by solar magnetic activity, and it is felt through currents, radiation, and drag. The most dramatic drivers are coronal mass ejections. A CME is a huge cloud of magnetized plasma launched from the Sun's corona, often associated with filament eruptions and flares. It can carry billions of tons of material and a powerful embedded field. On coronagraph footage, a CME looks like a bright halo swelling outward, as if the Sun exhaled. The inner corona dims where the mass left, an evacuated cavity. Farther out, the shock front can form, compressing the solar wind ahead of it. CMEs are not the only hazard. High-speed streams from coronal holes can also drive storms. They are less explosive than many CMEs, yet they can persist and recur as the Sun rotates, striking Earth again and again on a roughly 27-day rhythm. When a CME reaches Earth, timing matters, speed matters. Most of all, magnetic orientation matters, because the embedded field determines how efficiently it connects to Earth's. If the CME field points southward, it couples strongly through reconnection. Reconnection is the gate that opens the system. Magnetic field lines break and rejoin, converting magnetic energy into particle energy and heat. It is not a metaphor. It is a measured process in space plasmas. Spacecraft have flown through reconnection regions and recorded the signatures: jets of plasma, sharp field rotations, and energized particles. The mathematics is electromagnetic, but the outcome is tangible. A boundary becomes a conduit. Energy then flows into the magnetosphere and down along field lines. It drives auroral currents. It heats the upper atmosphere. It perturbs the ionosphere in ways that can scramble signals. Auroras are the visible edge of this coupling. Particles guided by magnetic fields collide with oxygen and nitrogen, exciting atoms and molecules that release photons as they relax. Green often marks oxygen near 100 to 150 kilometers. Red can glow higher. Blue and purple hues trace nitrogen and denser air at lower altitudes. The curtains ripple because the precipitating particles are guided by field-aligned structures and because the atmosphere itself is moving. What looks like art is actually electrodynamics. Auroras also mark where currents close through the upper atmosphere. Those currents are part of a global circuit, linking magnetosphere and ionosphere through vast sheets of flowing charge. During storms, that circuit intensifies and shifts, and the disturbance spreads beyond polar latitudes. Geomagnetic storms are quantified with indices built from magnetometers on the ground. They track how much the field is disturbed over time, turning invisible dynamics into numbers. They are the heartbeat monitor for a system we cannot touch directly. Storms can last hours to days. They often include substorms, shorter explosive releases in the magnetotail, where energy is stored and then rapidly reconfigured. The tail stores energy like a stretched rubber band, then snaps into a new configuration. At Earth's surface, the key hazard is induction. A changing magnetic field induces an electric field, and that electric field drives currents in long conductors, including power lines, pipelines, and undersea cables. These are geomagnetically induced currents. They are not lightning. They are slow, quasi-DC currents that can saturate transformers, pushing them outside their designed operating range. Saturation produces heat, harmonics, and protective trips that can cascade. In a control room, the storm is not seen as a flash in the sky. It appears as alarms, reactive power swings, and equipment that runs hotter than it should. The physics is planetary, but the failure modes are industrial. History gives us a boundary case. In 1859, the Carrington event produced extreme auroras and telegraph failures across continents. Operators reported sparks, shocks, and messages sent with batteries disconnected, as induced currents powered the lines. That era matters because it shows what a strong event can do to a simpler system. Telegraph networks were the high technology of their day, stretched across landscapes like nerves. The sun found them, and it used them. Carrington is not proof that disaster is inevitable. It is proof that the sun can produce events beyond modern experience. It is a calibration point for risk, not a prophecy. We also have modern near misses. In 1989, a geomagnetic storm contributed to the Hydro-Quebec blackout. The grid collapsed within minutes, showing how quickly space can reach into infrastructure. That event also taught engineers what vulnerability looks like in practice. Geology mattered because ground conductivity shapes induced electric fields. Grid topology mattered because long lines and certain configurations amplify risk. The lesson was specific, not abstract. Satellites are exposed in a different way. Storms enhance radiation belts and inject energetic particles into near-Earth space, increasing the flux of electrons and protons that can penetrate shielding. Those particles can degrade solar panels and cause single-event upsets that flip bits. Some failures are immediate, like a sudden reboot or a sensor anomaly. Others are cumulative and silent, as radiation slowly damages semiconductors and changes material properties. A satellite can lose capacity over years, and the cause can be invisible without careful diagnosis. Space weather also affects satellite orbits through drag. When the thermosphere heats, it expands upward. Density increases at a given altitude, and satellites lose energy faster. After major storms, operators sometimes see the effect as unexpected orbit decay. Objects that were stable begin to drop, and collision predictions must be updated. Even tracking networks feel the change because drag alters trajectories across the catalogue. This is where the upper atmosphere becomes a climate story in an unexpected direction. The thermosphere is cooling and contracting over decades. The driver is not reduced solar input, the driver is increased CO2. CO2 warms the lower atmosphere by trapping infrared. In the thermosphere, CO2 acts as an efficient radiator because collisions are rarer and emitted photons can escape to space. It emits infrared outward, carrying energy away and cooling that high-altitude air. This is not a contradiction. It is the greenhouse effect operating in different regimes, one where trapping dominates and one where radiative emission dominates. The same molecule can warm one layer while cooling another, depending on density and opacity. Observations support this cooling and contraction. Satellite drag records, density reconstructions, and temperature measurements show long-term declines in thermospheric density. The signal rides on top of solar cycle expansion and storm-driven spikes. In long time series, you can see the breathing of the solar cycle, up and down, while the baseline slowly steps downward. It is a quiet trend, easy to miss in a single year. Over decades, it becomes unmistakable. The result changes orbital dynamics. Lower density means less drag. Debris stays up longer. Old rocket bodies and fragments persist, increasing collision risk and complicating space operations. This is a quiet vulnerability. We often imagine storms as the main threat to satellites, because storms are dramatic and immediate. Long-term contraction changes the background conditions that determine how quickly orbits clean themselves. The debris problem is not only about clutter. Collisions create more fragments, and fragments spread into new orbits. More fragments increase collision probability, and the system can move toward a runaway cascade if mitigation fails. So the sun brings two kinds of risk. Short-term storms can disrupt and damage. Long-term atmospheric change can alter the orbital environment, stretching the lifetime of hazards we already created. We return to the central question and keep it disciplined. What can solar variability explain about recent climate trends? What can it not explain, even if it feels like a tempting single cause? Solar output has changed across decades, and it has been measured directly since the late 1970s with radiometers designed for stability. Those records show cycles, not a monotonic rise that matches recent surface warming. The trend in total solar irradiance over recent decades is flat to slightly downward. Climate fingerprints also matter. Greenhouse forcing warms the lower atmosphere and cools the stratosphere, because more infrared is trapped below while the upper layers radiate efficiently to space. Increased solar forcing would tend to warm both layers more uniformly. Observations match the greenhouse pattern, not a solar-dominated one. The ocean is the arbiter of the energy ledger, as earlier chapters established. Ocean heat content has risen steadily through solar cycles, integrating small fluctuations into a clear long-term gain. Short-term solar variations create small wiggles, while greenhouse forcing drives the persistent climb. Volcanoes provide another check. Large eruptions cool the surface temporarily by adding reflective aerosols to the stratosphere, increasing albedo for a year or two. The climate system rebounds as aerosols fall out. The long-term warming trend continues, consistent with the sustained forcing. This is not a dismissal of the Sun. It is a placement of the Sun in the budget, with numbers attached to the placement. Solar variability is a real driver of year-to-year and decade-scale variability. It does not supply the sustained energy imbalance needed to explain modern warming. Now we address the most persistent speculative link. Cosmic rays have been proposed as a driver of cloud changes. The idea is that ionization could help form aerosols, which could seed cloud droplets and alter albedo. Cosmic rays are high-energy particles from outside the solar system. Some come from the Sun during energetic events, but most are galactic, accelerated by distant supernova remnants and other energetic astrophysical processes. Their flux at Earth is modulated by solar magnetic activity. When the Sun is more active, the solar wind